Hey guys, welcome back. Today's video is going to be on reactions of alkenes. Direct follow-up with the last video, which is on the preparation and properties of alkenes. So hopefully now you guys have a better understanding of how to make the alkenes. Now we need to understand, what do we do with them, right? How should we be thinking about them as a functional group, as a reactant, or as a reagent, right? What things can I change this into? What transferases are available? All that nonsense. Okay. So if you didn't watch the previous video, that's okay. I'll just give you a TLDW real quick, right? The main feature of the alkene is the pi bond, right? Pi bonds, which contain pi electrons. So alkenes as sources of electrons means that we can only do reactions in a certain way. If we think about the way that we've done reactions in the past, where we've added nucleophiles or bases, this is not really going to work, right? Because nucleophiles are sources of electrons and bases are sources of electrons. Well, alkenes, I mean, they're pi electrons. They are also sources of electrons. So we try to react these guys. What we're really just going to get are electron-electron clashes. These guys are going to hate each other. Nothing's really going to come out of this. So not really the best thing that we can do. Yeah. On the other hand, though, as we said, right, alkenes are electrons. So if we shift our like mind view, our mindset, that alkenes are not the electrophiles that we used in the previous unit, but they are nucleophiles, then we can start to see stuff. Because if we treat nucleophiles with, what nucleophiles want, which are electrophiles. So now let's consider, alkene and an electrophile. Well, again, electrophile is delta positive, nucleophile is delta minus. Those guys are going to like each other now, and we're going to see reactions. Very, very clever name we've come up for this. These are electrophilic additions because we're adding electrophiles to pi bonds. So not a very hard name to remember at all. And one thing we can kind of notice here is that alkenes are acting as electron donors, right, to electron acceptors. So we can think of alkenes as Lewis bases, whereas electrophiles are Lewis acids. So electrophiles are Lewis acids. All right. Now, if alkenes are reacting with Lewis acids, right? Take a quick guess, right? Like what, or not take a quick guess, but think really quickly. Like, what is that most common Lewis acid, right? What is everyone's favorite Lewis acid? Like, what is that thing you think of when you think of acid? That thing, hopefully, is the proton. So a very good starting system to think of, right? Like, what is a very good system to begin with on the alkene reactions is the H+ reactions, and that's where we are going to start. Cool. So another way of saying, alkenes reaction with proton, really we want to examine only the reaction with H+ and not much else. So we can consider this to be a concentrated H2SO4 system here. So concentrated H2SO4 H+. Okay, what is this going to do to our alkene? All right, so let's bring back our alkene here. I'm going to try using colors in this lecture. So let me know how you guys feel about that. I just noticed that, like I mentioned before, I do a lot of practice runs with these. I noticed that when I did my practice runs with no color, there was a lot of information on the slides and they were all kind of clumping together. So I'm trying to use this color to help like unclump them, hopefully to help this out a little bit. So I'll try to use color. Please let me know what you guys think and if it's helpful or not. Cool. All right. So again, concentrated H2SO4. All we're really saying with this is that we only have proton in this system. Proton and from H2SO4. So again, right, alkenes are sources of electrons, and so we want to grab protons with those electrons. That should not be the surprising part about this. But one thing to remember is that when we react with alkenes, right, and protons, even though the pi bond does extend across two carbons, and it might be tempting to think that both carbons would react with a proton, there's something inherently wrong with this, right? That inherently wrong thing is the fact that a proton only has one orbital. So it can't really make two bonds, even though both carbons in the pi bond are quote unquote reacting here. Okay, so when we react with protons, only one carbon can get the proton because the proton can only make one bond. So that means that either this carbon here, which we'll call carbon 1, or this carbon here can get, they can get a proton. Okay. Now, looking at this, it may not seem very obvious which one is the right answer, right? Whether it's carbon 1 or 2. And really, we can't solve that yet because this is not a complete picture. We're missing something. To figure out what we're missing, just remember, right? The pi bond here is taking a proton, right? And in this case, either carbon 1 gets that proton or carbon 2 gets that proton. So if we're forming a bond with carbon 1, in this case, that means carbon 1 got the pi electrons. For forming a bond with carbon 2 gets the pi electrons. That means that the other carbon in the pi bond lost electrons. So if carbon 1 forms a pi bond, carbon 2 lost electrons. How do we, notate a loss of electrons? We say that that atom in particular that lost electrons is a cation or has a positive charge. Or in this case, right, we are forming carbocations. Now, with carbocations, it may be a little bit easier to answer this question, but still take a second if you have to think about it, right? Which carbocation is the more stable cation of the two? Carbocations, again, inherently unstable. The more stable one is the one that's going to exist, right? The one that's likely to form. And if we need a reminder, I'm totally willing to give it, right? A reminder on what is a more stable cation is going to be the more substituted cation. Okay, so cation stability in the alkyl series is going to be increasing with substitution. Reminder that this is governed by hyperconjugation, which is just a fancy way of saying that, we have carbons donating electron density towards these cations, right? And the more of these, interactions that we have, the more stable we are overall. So that's hyperconjugation helping us figure out this part of the stability series. Now, keep in mind that hyperconjugation is not the only thing that can stabilize cations. You can also stabilize cations with resonance. And these cations tend to be more stable overall compared to hyperconjugative stabilized cations. Okay, so if we need a bit of a reminder of stability, here you go. I know that it's not always taught this second part, but it is something that's still very important to know, which is why I'm going to include it. You guys definitely need to know this, that the more stable cation is not always the hyperconjugated proton, right? It could, or cation, it's going to be the resonance stable cation. Cool. In this case, I mean, both, there's just primary versus secondary carbon. So it's hyperconjugative here. Very, very easy choice to make. It's always going to be that our secondary cation is the one that forms more easily. Cool. So reacting with proton turns our alkenes into cations. And cations aren't new, right? Back in 118A, we learned a whole class of reactions that did cationic, formed cationic intermediates, right? Those reactions were the SN1E1 reactions. So now that we see that alkenes can form cations, we can think that quite a few of our alkene reactions are going to be governed by SN1E1 or unimolecular mechanics in general. Okay, and specifically, right, between these two reactions, if we think about our system at hand, we have HSO4 minus after reaction. Right? HSO4 minus specifically corresponded with one of these reactions. Again, don't take more than a second to think about it, because if you don't remember, I'll just remind you. HSO4 minus was what we considered our eliminatory acid, or E1 acid, right? Again, I mentioned, or maybe I didn't, well, I'll mention it now. H2SO4 concentrated is commonly thought of as a non-nucleophilic solution, and non-nucleophilic solutions were the best solutions to have if you wanted to do elimination reactions, especially like E1. Okay, so HSO4 minus is just going to perform an E1 reaction that forms an alkene. And so how does E1 work? Next to the cation, this carbon and this carbon here, we have hydrogens. HSO4 minus can choose either of the hydrogens to react here. But in this case, right, both of them are the same, right? I nitpicked this example to be symmetrical. So we can just react with one of them and we'll get the same answer anyways. We can take this proton here. Oh, went way too far there. Okay, we can take this proton here, and what we form is an alkene once again. And actually it's the same exact alkene from the beginning. Okay, cool. Now, one idea that we can get from this that might be new to you guys, because we haven't really used this term before, but notice how, right, this reaction was governed by cations. So the most stable cation that formed sort of dictated what the product was. The fact that both carbons were different in the pi bond, right? Carbon 1 is secondary, carbon 2 is primary, and that difference in carbon type dictated which product we got is something we call regiochemistry. So this term, again, what does it mean? It just means that different regions or different parts of our molecule react because of some chemical reason. So the reason why carbon 1 reacts with, the reason why carbon 1 forms the cation and carbon 2 does not is because regiochemically, it is a secondary carbon and that's more stable for our cationic intermediate. So we'll be using regiochemistry quite a bit as a term and to explain a lot of things. So expect it to come up in most of our reactions. Just wanted to introduce you guys to that term because sometimes I'll use it, but I won't explain it and people will be confused. Okay, cool. So I'm just going to redraw our reaction down here, but without all the colors, just so we have it, right? But again, one thing we noticed was that if I reacted, let's say 1 propene, I would form, right, the regiochemical carbocation, that more stable secondary cation. I'm also going to try to label all of these so it's, again, easier for you guys to see what we're thinking about, right? Carbon 1 gets the cation because carbon 2 would not stabilize that cation very well. So you can kind of pull out, sort of a rule here is that if both carbons are regiochemically different, right, in this case, a secondary and a tertiary, right, that means then, actually, let's use this example. Let's say we had this here, an even more, extreme example. If we have 2 different carbons, right, in this case, we have a tertiary and a primary. If we are to form a cation, it is going to be on the carbon that stabilizes better. In this case, tertiary versus primary, it's always going to be the tertiary that forms the cation. But these cations themselves, right, it's not exactly the most stable thing on the planet. They're going to collapse back into an alkene. In both of the examples, right, we can collapse back to the alkene. That is the more stable alkene. Okay. So then the question becomes, what if I have an alkene where there is no difference, right? So let's take a butene, for example. If I react with H2SO4, carbon 1 and 2 are not regiochemically different at all, right? Carbon 1 and 2 are both secondary. So if I form a cation, we'll form this one here, right? The other cation, which is this one here, is of equal stability. Both are secondary. In this case, we're lucky because this is a symmetrical alkene, and symmetrical alkenes form, identical cations regardless of where you react. So we don't only have to really worry about one of these guys. So again, this cation could collapse back into the butene we see here, this anti-butene. But if I have, let's say, this guy here, where it's asymmetric, we will be forming 2 different cations, right? Again, although they are the same stability, they are different, right? One is in the middle on that 3rd carbon, and one is right on the side with that 2nd carbon. Once again, we can remove the same protons that we added. So this H here versus this H here. Apologize for that crampness, but those H's there, just remember those, right? We could remove those to reform this alkene, totally possible. So let's consider the isobutene. Let's consider the 1-butene system where we can protonate, right? Once again, we see a stark difference simply because of regiochemistry, right? Carbon 1 versus carbon 2, carbon 1 is more stable. And carbon 2 gets the proton. And again, we can kind of say that, okay, we can take off this proton here and go backwards in time. But there's something interesting here, right? This proton is different from this proton here. Okay, so I know that there's like 2 other examples here where that was the case, but we're going to focus in on it now on this one, right? We have an HA here and an HB here, right? And HA gives us this alkene, right? But HB is also a proton that's here and it's different. So how do we deal with this one? Well, let's just see what the product is if we take off HB. Taking off HB gives us this alkene here. Right? Both are butenes, but they're isomers of each other. They're different types of butene, right? This is 1 butene, this is 2 butene. Now, another real difference that we see here is that if I were to look at this alkene has one substitution on it. This is a monosubalkene, and this is a disubalkene. So in this case, where we get 2 different alkenes, which one is the better alkene? Or is there a better alkene, right? Which one do we think? So take a couple seconds. I think if you watched the previous video, you might know which one might be better or which one might be worse, or if there even is a difference. But if not, just take a couple seconds, maybe even just lock in a guess. Is it the mono or the di, right? So 50-50, you got to get it wrong or right. So just lock in a guess. And so the best way to explain this is to think back to our regiochemistry idea, right? Remember how in regiochemistry we wanted the most stable cation, right? The system formed the most stable cation. Well, in the same way that we want to form the most stable cation, if we were to choose between which alkene is better, we want the more stable alkene. And how do we choose, what is a more stable alkene? Well, I'll give you a bit of a hint here. We have hyperconjugative forces for every sp3 carbon that's on a pi bond. In this case, we have 1 force. In this case, we have 2 forces. So which alkene is more stable? The more stable alkene is going to be our disubalkene. And so with that in mind, that must mean then that our 2-butene or a disubutene is the guy that's the one that's favored. So this is interesting because this is an alkene that is not the starting alkene. All of our examples have tended back towards our starting alkene. So it's almost like no reaction really happened, right? But there was a concept that we can form cations and reform that same alkene, right? So all these guys tended to be on the left side here, right? In terms of if there was a reaction, it was just back to the same alkene. Right? Oh, sorry. I erased the wrong arrow on these guys. I'll go back and do this later. Anyways, like I was saying, if we were to think about which alkene were better, it is clearly going to be the anti-butene. So alkenes, not only can they form cations and reform the same alkene, they can actually isomerize to their more stable counterpart. So one thing to think about then is that reactions that can happen in non-nucleophilic acid is alkene isomerizations. We can actually see there's actually a very good example of this. One that, it might not have been very obvious, but might be obvious now. But if we have, let's say, syn-butene, and we react syn-butene in acid, again, both these carbons are the same. So they're equal in stability. So it doesn't really matter which cation we form. It's also symmetrical. So it also doubly doesn't matter which one we form. But with the, the removal of the double bond, right? Double bonds can't rotate, but single bonds can, right? We can rotate syn-butene into its anti-form. And from this anti-form, we can form the anti-butene. So even syn-butenes, or even like equally substituted alkenes, can tend towards their more stable variant of that equally sub alkene. Now, if I were to take, let's say, all 3 of these alkenes and dump them in acid and leave them overnight, a really cool thing happens, right? One is that all of it reacts, right? And we kind of get an idea of distribution. But what do we see in terms of distribution? How much of each form do we see? It's very, very stark. We see 95% of the anti-form, about 4% of the syn form, 1% of the terminal form. So very, very, very obvious distinction here between all of them. There is no ambiguity. Clearly, the system tend towards stability. So not only, so technically, yes, this guy can go to this guy, but then this guy will quickly isomerize into the anti-form. Okay, so alkenes in acid and simply just acid, non-nucleophilic acid, will tend towards stability. So let's say I have this alkene here, right? Once again, if I were to think about the alkene, or sorry, the cation that would form, you would get this cation here. And once again, we just ask ourselves, which proton is better, right? It's going to be the proton on the left side. And what we get is a really nice tri-subalkene just like that. Okay. We also were kind of, taking for granted that notion here, where we were just kind of forming, the same alkene over and over again, even though technically in this example, we could have formed that one propene. Well, it's like our intuition kind of knew that we want to go here. We want to go towards more stability. Stability is really nice. Lower energy content is always better than higher energy content. Okay, cool. Now, this idea of tending towards stability is not really new. It's not novel, right? Because back in 118A, when we considered, again, SN1E1 reactions, cations also very commonly tended towards stability. So let's say we have this alkene here, right? And this alkene, right, we gave it acid. I'll use H plus now, just because I'm getting a little lazy, but just think concentrated acid with no nucleophile in sight. This is really important. I've been emphasizing this point for a reason. So I don't think I'm just saying that for no reason a lot. I'm emphasizing that point for a reason, that this is no nucleophile present, okay? But we're gonna form, obviously, the regiochemical, let me label these, sorry, I forgot to do that. But we're gonna form the regiochemical cation, right, which is the secondary cation. But again, when we look at this cation, next door, there is a quaternary position. And if there is a secondary cation with a highly substituted position next door, or a branching position next door, we always commonly see rearrangements. Okay, so this is like another form of isomerization, right? Alkene, you can think alkene isomerization or alkene rearrangement, right? I think maybe rearrangement would be a better term, but I'll keep isomerization for now, right? But this guy is going to methyl shift. So I'll put methyl and shift here. Okay. Methyl shifts, sometimes people have a hard time seeing how to do them. So I'll offer you guys an easy way to do them. Just redraw the same structure. One of these methyls is going to shift, so erase one of them. In the place of that methyl, we'll put a cation. Then just take that methyl, you just erase it and put it where it should be going. It should be going here, so put it there. And there you go. Methyl shifts, super, super easy. Now that we formed this shifted product, right, or this shifted intermediate, it's very easy to see where that really nice alkene can form. It's going to form right down the middle there. Okay. Again, cations constantly rearrange. So why can't alkenes rearrange if they can, become proton? And so once we kind of understand this idea that alkenes can isomerize, a great follow-up question is, how far can we take this idea, right? How much can I abuse this isomerization mechanism? So here's the system that I'll offer to you guys to think about. But let's say that we have this alkene here. Okay, sorry, I'll be constantly formatting things, just moving things over. So I apologize now for that. It's just, ease of viewing. And just because as I'm making these slides, I always forget how I want to format these, but I remember in between. So let's go ahead and move those there, so we have a little more space for this one. But hey, let's say that we have this substrate here. Again, shouldn't surprise anyone when we form this cation here, right? And so again, we can ask ourselves the question, if we have this H and this H, right, which one's the better one to form the alkene again? It's definitely going to be the one on the right. So we'll form that guy there. Okay. Oh, sorry, the alkene. Now we do have, a better alkene. We went from mono subterminal to, internal anti-alkene, but it's not like when we're in acid, we only react once, right? We're constantly in acid. Like we saw here, like I mentioned, if we threw all three of these in, all three of these tended to react towards the anti-butane. So alkenes, right, if they can react, they will, and they constantly will until they're the most stable. So what's the point that I'm getting at here? Well, let's say that we protonated once again. And so it is true that we can make two cations here because both of them are the same. One cation goes back this way and we don't really care about it, but the other cation goes this way. And once we form that alkene, what do you notice? We notice that there is a very nice spot here, and that means that where are we going to form our alkene? It's going to be right across there. So alkenes will literally walk down the carbon earth, right, or the alkane earth, the alkane skeleton, just to get to that most stable position. And so we can form and reform double bonds as much as we want to get to there. Now, one thing people always say is, how do you know, again, how does it know it's going to go here and not here? And the thing is that we don't. We're just hoping that, eventually it starts to go towards this way, right? And we form the double bond. Also, even if we did form this carbocation here, it's always going back here. So it's like these guys are constantly equilibrating between these two, and then accidentally one time it'll go this way, and then it will be sucked in to go that way. Like it'll just be trapped and going towards the bottom here. One last thing that I'll note here is that you could also have proposed a different mechanism to go from here to here. It's one that people are less comfortable with though, which is why I always show this one last, but we could have also hydride shifted, right? That's totally possible too. Hydride shift could have happened. It is that people are not very comfortable with secondary to secondary shift because they feel like it's, you know, it's taboo or it's like not allowed. In reality, it is allowed, right? But it's just, you know, some professors, they like to teach very strict rules, like this is the only thing that can happen, right? So only do this, or, you know, sometimes it can happen, sometimes it can't. I will offer you the ability to choose whatever you want to do, right? With these reactions, but either one of these are acceptable, whether we want to do the hydride shift or we want to do the more, you know, straightforward form alkene, you know, destroy it. Oh, sorry, form cation, just form alkene, form cation, form alkene. That totally works. So one last problem that I'll leave with you guys on this page that you can think about, you know, pause and think about it for a minute if you have to make sure you're understanding what's going on here. One thing we can think about is how would the following react? So terminal alkenes are like sort of the diagnostic, or they're sort of like the, you know that they want you to do an isomerization reaction if you see concentrated acid in a terminal alkene, because terminal alkenes are, if it's not one propene, right, or just propene, if it's anything else, it can probably rearrange. I guess isobutane can't, but these two examples are really the only ones I can think of where you can't really isomerize the alkene, but any other terminal alkene can be isomerized. And so go ahead and think about how you would do this one. Maybe pause and try this for like a minute or two. Cool. So hopefully you guys tried it out. The main thing to really take away from this is that none of you should have been drawing any sort of intermediates, because again, alkenes, like we mentioned with this example, they can walk all over the alkane chain. You just have to figure out where the best spot is. So once I form, or once I add acid, you can think that there's like this partial double bond character going all around this molecule. You just got to figure out where the best partial double bond is. If we look, right, if I just erase this, just go with your pencil and draw in where you think the best alkene is, right? Where is the best alkene? Should be kind of a no-brainer, right? Terminal, tri, di, tri. But there is this nice tetrasub down the middle. That's where alkene is going to go for sure. Now, there's one extra level of complexity in this problem that I wanted to bring in, because this molecule here, oh, sorry. So I'll change this now. I apologize now because you're probably not going to get that added complexity when you were trying this on your own, but I'll add this complexity now so you guys can think about it. But with this added complexity, there are now two different isomers that are available, right? This isomer here could have formed, but we could have also have formed this isomer here. So just to remind you guys, this one that looks like it's a syn isomer, we call Z, and this one that looks like the anti-isomer, we call E, right? The like groups are syn, the like groups are anti, right? Z and E. And I'll tell you, only one of these forms in a very high quantity. So take a guess which one you think it is. Don't think about this for more than 1 second. I'll tell you, there is some data on this page that tells you which one's the right answer. And the right answer is going to be E, right? Because E is sort of like the anti-alkene, which we saw over here. The anti-alkene always likes to form. And so again, in acid, we're going to stabilize towards the, we're going to move towards higher stability. And so E alkenes, best example of more stability. Cool. So if you got that right, that's great. That's great. And this is what you want to think about for this kind of solution. Now, again, I emphasize so much about this idea that there has to be no nucleophile, no nucleophile, no nucleophile. So what happens when we do have nucleophiles? Because again, alkenes forming new alkenes, that's not a really fun idea, right? We don't want to get rid of the alkene, but we want to functionalize it. We want to do something with it. So what happens when I have, nucleophiles? A great starting nucleophile is if I just take my concentrated acid and just make it dilute. Or in other words, right, I use H plus H2O. So water is going to be our first nucleophile that we're using to use to transform our alkene. Okay, cool. So go ahead and start this reaction off much in the same way that we did the last one. It's not much different there. And if you'd like, by all means, don't feel like you have to follow my pace. You can always skip forward ahead if you need to. But again, we can attack that proton. Actually, how did I color scheme this? Okay, I did it the same one. Again, won't go over the regiochemistry, but we should hopefully understand why now. We do want to go towards, that more stable secondary cation, not the primary. But now when we're at this point, right, we have two components in solution. Before we only had one. We only had H+4 minus, and we said that had to be eliminatory, right? Because it can't be a nucleophile. It's not, learn as a nucleophile. But now we also have water. And if you weren't already aware, I'll tell you now, water is a better base and a better nucleophile than H+4 minus. And in this case, it's going to act, straight up as a nucleophile. So we're going to have our first nucleophilic addition across a pi bond, and that addition is going to be the addition of water. Now, water obviously adds protonated. Something in solution will pull off that proton. And what we're left with is an alcohol. So this reaction has a name. We call this hydration. Anytime you form an alcohol on a pi bond, this is a hydration reaction. Okay. And once again, regiochemically, most stable alkene forms. Or sorry, most stable cation, not alkene. But you guys get my point. Most stable cation is the one that forms. Okay, cool. So a lot of the mechanics of the previous set of reactions is also going to apply here. Once again, I will add in the example we did up here just with less complexity. And I'm just going to refer to these as H plus H2O, but just keep in mind that dilute H2SO4 or, seeing H2SO4 doesn't change anything. Maybe actually if I do a couple of these with H2SO4, it will be helpful. So H2SO4, H2O, or H2O, H2SO4 doesn't matter, but we're going to form that regiochemical cation, and alcohols are going to form. So I can take those first two examples, and you guys can try these too if you'd like. Shouldn't be too difficult, because all we're really doing, it seems like, is we're adding an OH to the carbon that stabilizes a cation better. Right. So what we get is 1, 2, 1, 2. I think what I'll do is I'll also draw the cation intermediates. I think it's good to see the intermediates. They'll help you out. So I'll take the extra time to do that. I imagine most of you guys are going to watch. If you're going to watch this, is going to be in accelerated time anyway. So by all means, please accelerate the time. Don't feel like you need to go by pace unless you need to. Okay. Once again, if there is no regiochemistry, right, as is with this example here, right, because either cation could form here, then we're going to form two cations. But in this case, again, both cations are the same, so it doesn't really matter which one we form. But there is something else we can worry about here. Look at this a little bit. What do you guys notice? This alcohol is chiral. This is a chiral alcohol. So how exactly are we going to address chirality in this class? This is very simple. If you just remember in SN1, E1, how carbocations in general reacted. But if we form a cation, that's an empty p orbital. Water is just going to interact with it. And in this case, water can interact from the top or it can interact from the bottom. Really doesn't matter. There is no driving force to tell us, but we are going to get both the dash and the wedge product. So we can also label these if we wanted to. This is the R and this is the S, right? If we're forming molecules where we have the exact opposite stereochemistry present on each molecule, so the exact opposite, this is all R and this is all S. These are enantiomers, right? And enantiomeric mixtures, right, we call racemic. So we could have also had said that these were racemic. Okay, so we will have racemization of the carbocation center that we react with. Now, don't believe that every single reaction is going to be racemic and just write racemic, because keep in mind, all we're racemizing is the cation we're reacting with. So what's an example of where we won't see this exactly? Very, very nice one I can draw here. I know I'm drawing a fairly complex one, but you'll understand why I have to do this, hopefully, as we continue on. But I can take this guy here, I won't draw the cation just, for sake of space. But if I were to draw the two answers here, right, I would have this alcohol. I would also have this alcohol. And so again, what do I notice? There is a racemization of centers, right? The center that reacts, the cation we form, that is the center that does racemize. But notice something else on this molecule. There is a center here, and that center stays the same, right, in both products. So, I mean, what is this? I think it's 1, 2, 3. So this is R. This would also be R. And again, enantiomers have to be complete opposite of each other. So if this is R, this has to be S. If this is R, then this will have to be S. But in both cases, there are. So if we have an incomplete inversion, or we don't have like all stereocenter slipping, these are diastereomers, and no longer is this a racemic mixture. This is not racemic. This is diastereomeric. So please don't make the mistake of just assuming everything is racemic. It is not always going to be the case. My best advice to you guys on this is just, if there is a pre-existing chiral center, right, that tends to mean that they're looking for you to draw, diastereomers. Another thing is that if you just don't write racemic and you just write all possible answers, you never have to run into the issue, because racemic is really used when we draw like a planar form. We put racemic so the person reading knows. If you just draw both of these, it's the same thing as saying racemic. So ways to make sure you don't lose out on points because you knew the concept, you misused the term. Cool. Now, one idea that we kind of talked about last time was the idea that we could have like no regiochemistry, but on asymmetric alkenes. So this is a symmetric alkene, but let's say we had an asymmetric one. On asymmetric alkenes, again, we just form two different carbocations, right? I guess you could say this is regiochemical as well, but regiochemical simply because they're not the same. And so one of these cations is really easy to resolve, right? This bottom one here is very, very simple to resolve, because when we add our alcohol to it, who cares how we draw it? This is achiral, right? Two ethyl pieces coming out of this carbon, achiral, so who cares? But this guy here is a little bit harder to resolve because, this does form a chiral center. Actually, I guess it's not too hard to resolve. We know it's going to be racemic, right? So this is also going to racemize. Could label, right, that this is racemic. This would be R, this would be S. Cool. So again, we're going to form quite a bit of product in these reactions. Now, recall that, if we form cations, that means that inherently cations unstable, they want to be stable. So what about those examples where we had like sort of rearrangements or moving of things around? That can totally happen here too, right? Because let's say we had this guy here and we formed the cation, again, regiochemical. I feel like if someone tracked how many times I say regiochemical, it's probably going to be in like the thousands. So I apologize. It's just a very powerful term. But when we have this cation, right, this cation could rearrange. We could have a hydride shift occurring here. And so how do we draw hydride shifts? Very simple. Just draw the same structure and put the cation where you need it to go. Hydride shifts are super simple. And the alcohol could totally add here. A great question from this is, okay, so in non-nucleophilic acid, it makes sense why the cation can move all at once because there's no nucleophile to capture that cation. But what if we're in nucleophilic conditions, right? Is it possible that maybe the alcohol captures here? And the answer is yes, it is. It is very possible for the alcohol to capture before it rearranges. But remember that water is very, very, very weak nucleophile. It kind of sucks. So it takes a while for water to actually be motivated to attack as much as, a stronger nucleophile. And that means that there's a lot of time for, this cation to rearrange. So in general, it's not that we're not going to see non-rearranged products, but we're going to see a lot of rearrangement if we use weak nucleophiles like water. Water is weak, so there's time. Definitely a lot of time to do these reactions. It also means that if we did the, the tert center version of this, you should expect to see sort of the same thing, right? Once again, how do we do this? Erase one of the methyls, put a carbon in its stead, and then move the methyl where we're, we're moving the cation in the first place, right? And there you have it. This turns into this alcohol here. So again, water, a lot of time that we have to have these rearrangements occur. Okay, so don't be afraid to do rearrangements with the alcohols, with these alcohol products, I should be saying. Now, with these rearrangements, there's also then the conversation of like how acceptable is a rearrangement? Because if we take that same example that we talked about before, where, right, we saw here in this example, right, we can form this cation, and then in the previous slide, right, remember this cation kind of moved around. You know, how likely is that going to happen here? Because if we want, you know, a movement, right, we'd have to do a secondary to secondary shift of hydrogen. And then maybe we get the tertiary shift of hydrogen, right? So shift here, and then we get there. So great question is, you know, is it likely, is it very likely that we're going to get this kind of movement? And the answer is, it's really professor dependent. So like I mentioned, some professors like to keep it simple and they tell you, no, secondary cannot go secondary, right? And some professors are like, hey, I want you to think about it, right? I want you to tell me, right? I want you to think, can that occur? Can it not? And so this is always a better question to ask your professor than for me to answer, because every professor is different in how they think. Some professors might tell you, yeah, you know, if you can tend towards stability, we will do it. And so again, water being a weak nucleophile, maybe you can make that argument, it has enough time. Right. Other professors are just like, hey, you know, I want you to not have to worry too much. Just make the alcohol, right? Only rearrange it, like only rearrange the product if it's right next door. So by all means, ask your professor what they feel like, because again, they're the ones writing your keys, grading, you know, your exams. They'll be the ones that determine whether or not it rearranges. In my opinion, it's more important that you understand what's going on and why certain things are allowed, right? Again, in acidic conditions, we can do a lot of things. I mean, we could totally form this alcohol here and have, you know, this product, but we're in acidic conditions. What's stopping this alcohol from protonating and going backwards? So a cool thing here is that, you know, again, even alcohols can equilibrate. So all these arrows should be, you know, like this, right? This is an equilibrating reaction. Alcohols, as we learned, have the capability of being protonated, and that protonation allows us to, you know, switch stuff around. So if you want to make the rearrangement, you know, argument, I would use this in my argument, right? That cations, right, or the cations can really form from alcohols as well as alkenes. So there's always a, you know, plethora opportunity. Maybe it might be up to how much time you let this sit, right? Maybe if you let this sit for a really long time, you give it enough time to isomerize all the way to this point. Again, just do, you know, your due diligence and get an answer from the person that grades your exams. Okay. Otherwise, you write the answer that you feel more comfortable with and argue for it if it turns out your professor doesn't agree, right? It's all about your chemical thinking that will get you, you know, points in this class. Cool. So these are the reactions with weak nucleophiles. And actually, there's one more weak nucleophile we can consider here. And I just realized I forgot to talk about it, so I apologize, but I'll put it here. Alcohols are organic water. And so if they're organic water, they should do the same exact reactions as water. Maybe not the same exact, but they do similar reactions as water. So I'll put this one here because we already have it up here anyways for water. For alcohols, if you react, we get ethers. So both alcohols and water can do these reactions. And these are the weak nucleophile reactions. So what if we use something stronger? Right? What if we use a stronger nucleophile, like HX? Right? HX has, you know, halides, and we learned halides are pretty good, right? All things considered, they're pretty good. And we can draw our alkene here. Proton gets taken. That's not the part that surprises anyone. We've been doing this a lot now. The part that shouldn't be too surprising, but is new, is that now we have X minus, and what do we think captures, right? In this case, it's going to be X minus that captures. X minus is going to capture. So, I mean, if we look at this reaction, notice that nothing really changed too much, right? The reactions are kind of the same. All that really changes is what's the nucleophile. So these reactions are completely related. Only difference is what nucleophile do I use, right? For the reaction. That's the nucleophile that's going to dictate the product. So we call these hydrohalogenation. Hydro because of hydrogen and not water. That's a very confusing thing. I've always found that confusing. I never liked that. But that's what that, you know, hydration, even though there's a hydro means hydrogen here. Okay. But, you know, I want you guys to think about these examples here that we've done and realize that we have the same exact answers pretty much. It's just halogens instead. So I'll write out a couple of these just for writing them out, but I won't write out all of them. And we're going to go through them a little bit quickly, right? Because nothing's really different here, right? If I have this cation here, let's say I did this reaction with HBr, right? Then I should just have a Br here. It's not different, right? If I have that regiochemical example, right? That lack of regiochemistry example, like this one, right? Where we can form two cations, right? Both of these cations can react, right? Let's say we did this reaction with HCl. So we get Cl minus here. So we get this here and this here. And once again, right, if I have a product that could be potentially chiral, that's just going to be a racemic product. So hopefully nothing new there, right? Then it just brings us to, okay, what about rearrangements? And rearrangements can also occur, right? We can also consider if a rearrangement occurred. So let's just use this example here. Form this cation. Cation rearranges, and your halide can capture. Now, I'm going to use X here very generically for a second, because there is something there's something that we can talk about for a couple minutes before we move on. And remember, when we talked about rearrangements on the previous page, I mentioned that, water being a weak nucleophile really helped out a lot, right, in making sure that we could have enough time for the rearrangements. That's why I said that the rearrangements are very likely to occur, because we have a weak nucleophile. But what about halides? Halides are definitely stronger nucleophiles, more likely to do, more likely to react faster, right? More likely to mess things up. How might the halides be, in terms of rearrangements? And so I'll give you a couple of data. Like, really the only way to know is to look at the data, and that data is, hidden in like these really old German papers that, luckily for you guys, I've already tried to read them. But it turns out if I use a different halide, I get kind of a different result. And so of the halides, hopefully you guys know this. If not, I'll tell you. HI is the best halide in acid. HCl is the worst halide in acid. So if I use the best nucleophile and I look at the product distribution, right, for rearranged and non-rearranged. So let's actually draw both of them. So this will be the rearranged here. So I'll put rearranged here, and then let's put the non-rearranged product here. Okay. What do we expect as a product distribution? For iodine, it ends up being a 50-50. And, this shouldn't be too much of a surprise, because once again, like, iodine is a very good nucleophile. So if we form the cation, right, iodine's going to be nearby, it's going to probably capture that cation very, very easily. Now, sometimes it gets a little bogged down by the protic sulfate, and maybe the rearrangement can occur. Turns out it's about 50-50. Okay, so both products are major. And hello. Sorry about that. Mic went out. It's probably going to go out a couple times like last time. Apologize. Anyways, back into this, right? This should not be surprising, because halide, I is the strongest of the nucleophiles, and it turns out 50% of the time it rearranges, sometimes it doesn't. So both of these are major products, and they're both something we should consider. If we look at bromide, interestingly enough, the ratio goes from about 50-50 to about 52-48. Okay. Now, bromide, it's a little more easily bogged down, but still it's about 50-50, a little bit in favor of the rearrangement. For chlorine is by far and large like the worst of the halides. The ratio, if I remember correctly, goes to about like, I think it goes down to like 56, I think. 56-44. Okay, so how do we make sense of this data? What is this data really telling us? The way that I see the data is that clearly there is rearrangement, and clearly there isn't rearrangement, right? There's a good amount of both products, right? So when we're on an exam, for example, or we're doing practice problems, right, and we're thinking about what the answer should be, right? What answer should we put, or what answer should we think? In my opinion, you should think both. But the really important thing that I would think about is the fact that in any case, rearrangements tend to occur if they can, right? If a problem looks like it can rearrange, right? It can make a cation that kind of can rearrange, it will rearrange. There is no doubt about it. That rearrangement is going to occur. Don't just try to, bog yourself with the idea of like, oh, it's a strong nucleophile, maybe it won't, maybe it will. The idea is that it will. So you're always safe thinking that the rearrangement product can exist. Now, don't just eliminate out the non-rearranged product. It's still a very, important one, but just keep it in the back of your mind. Again, most professors, what they'll do is they'll, in an attempt to make their class easier, is they'll just require you to put, like the rearranged product or, again, professor dependent. Do they want both or not? But in most cases, if a product can rearrange, the point of it is to see if you will do it, right? That's what they're testing you on. I just wanted to introduce this data to you. I think it's important to recognize, right? Again, alcohols and water, weaker nucleophiles, so we don't have to worry too much about like how much the distribution is. It's very highly, in my opinion, in the side of the rearrangement. But when it comes to these halides, stronger nucleophiles, it can be a little bit different. Okay, cool. So like I said, I mean, we went through this pretty quickly, and it's because a lot of the reactions are quite literally the same. There really isn't much of a difference between, halide and water, other than that little nitbit that I put there. That's really the only big difference. So I'm going to use the rest of this page to kind of highlight some interesting examples, mainly examples that concern, right, the stability of cations, right? That's a big thing here. We talked a lot about how regiochemically cation stability is what really matters. And that's always going to be the case. Right? We're always going to make the most stable cation if we can for these acid mechanisms. Okay, so a very cool example of these, cations that are, can't always see that they're more stable are going to be from our shapes. So I'm going to, use primarily the square here, right? But what I really want you guys to think about is a triangle and a square. Back in 118A, we kind of talked about these guys. And if you didn't, it's okay. I'll just tell you what you need to know about them now. Triangles and squares they really hate being themselves. They really hate themselves. And the main reason for that is because triangles and squares are super strained. They want to very much be the next shape in the series. So triangles very much want to be squares, and squares very much want to be pentagons. So whenever you see a triangle and a square, you should think about if there's a possibility to make them, the next shape in the series, because if they can, they will. Like without a doubt, they will become that next shape. So what's the way that we can do that? Let's say I took this square and I added just H+. Doesn't really matter what kind of H+. There's 3 different forms we've learned, right? Concentrated, dilute, and halide acid, right? But let's say that we just added any acid. The first part is always protonation anyways. So you get to here. Now this is a secondary cation next to a tertiary center. So you might think, oh, okay, that's just going to rearrange, right? Or maybe it might just form a double bond, right? Because that's what we learned about concentrated acid. Well, here's the cool thing. I mean, you're not wrong to think this is totally great because that's what you've learned. But again, if a square can become a pentagon, it will. And this is actually what's going to happen. This square is going to expand. Crazy, right? So crazy. So how does this expansion work? So again, like I said, square is going to pentagon. So we can already draw the pentagon. We know that's going to be the basis of our shape. And so what's that 5th atom that becomes the pentagon? That's going to be this carbon here that we're attacking. So how do I know which carbons are which? Well, you can see 1, 2, 3 kind of all stay in the same space. Actually, I'm going to change this numbering a little bit. Let's do it this way. 1, 2, 3, 4. That's a little bit easier to see. Okay. So that would mean that this is 1, this is 2, and this is 3. Those guys stay the same in this reaction. What's really changing is that 3 and 4 are losing their bond, and 3 and 5 are forming a bond. So another perspective you can take on this, if it helps, is you can draw this like this. And you can say that 3 and 4 are losing their bond because that's the bond that's breaking, and it's forming between 3 and 5. So 3 and 4 lose it, 3 and 5 form it. Okay. If 3 is forming a bond to 5 now and it lost its bond to 4, that means that this carbon over here is not 4, it's 5. And that this carbon here, that's 4. Okay. So this is how you can, if you want, you can use this. This is how you would, label out which carbon is which. Just keep in mind, right, carbon 5 had a methyl, so we should put a methyl there, right? Carbon 5 is a methyl coming out of it. You can kind of see it here. I think people like this method a lot, so you can use it if you want to. And then you can just label carbons here if you'd like 1, 2, 3, 4, 5. Doesn't matter how you do it now because it's just a matter of, turning this into this. Now, one last thing we need to remember is that, a rearrangement, all that really does is, all that a rearrangement does is it changes the location or the shape. There should still be a cation on here. So where does the cation go? A lot of people mistakenly put it on carbon 5 because it's tertiary, but keep in mind, even though 5 did, have a cation before, 5 formed a new bond with 3. So it has the electrons now. It can't be a cation. On the other hand, 3 broke its bond with someone. It broke it with 4. So if 5 gained a bond, if 4 lost a bond, where should the cation be? It should be on 4. So the cation here will be on 4. And so if we're in, let's say, concentrated acid, which is the best, I think really the best way to ask this question is in concentrated acid, we will form the stable alkene from this, the most stable alkene. Okay. Notice how this is way better than that alkene from before, because this is terrible. I mean, the square, that hates to be a square. If you think about bond angles, this has to be 90 because it's a square. But remember, this has to be 120. So how can this be 90 and 120? It's really mad. It's not going to be happy. Terrible, terrible, terrible. Okay. On the other hand, this is a lot more happier, right? Because this bond angle here can be a lot more accommodating towards that. I mean, what is it for pentagon? I don't even know. What's 3/6 divided by 5? It's like 1. Oh man, I'm embarrassing myself. What is 3/6 divided by 5? I don't know. This would be 7. It's like 75. Is it 75? Maybe. It might be 75. Anyways, beyond the point. 75 degrees. Wait, isn't that worse? Okay, I'm clearly confusing myself. Whatever point I was trying to make, we're not going to make it. We're just going to forget about it. Apologize. Anyways, this is a lot better shape. You can also have a hydride shift, right? Towards that tertiary center, if we need it to do that. And then we can have a capture by a nucleophile. So you can think that alcohols likely, go down this pathway. Halides can too. But remember, halides are going to be 50-50 about for this one and probably capture on here. Again, I just want to make sure it's clear. Like, I don't want you guys to freak out about all these possibilities or anything. Again, if a product can rearrange, it's likely your professor wants you to rearrange it. So focus more on this pathway. I just mentioned this one because it's a good thing to talk about. It's a good thing to mention. Now, keep in mind, this is only true for triangles and squares. We're really not going to see this for pentagons going to 6-membered because pentagons are happy. All right, pentagons like being pentagons. So if we saw anything here, at most, it's going to be a hydride shift. And then we'll get capture a product, right? So we can get, if it's concentrated, right? So this is concentrated. If we have a nucleophile in solution, we might get this. And then again, sure, maybe we can capture from here. But again, don't worry too much about this. That was more of just a thought experiment that I wanted to bring up. Okay, cool. So these are the most significant examples you can think of for the cationic mechanisms. And we've really covered everything just in all that, right? Not much different there. Another useful strong nucleophile that can do these reactions is going to be sulfur. So, I don't know if you need to know that, but it's good to mention. Not a terrible thing to mention. Sulfur can do this too. Now, just like with the last section, where we talked about, an example that can help us make sure where we're tying everything in together. Actually, I guess these examples that I'm going to bring up, they're kind of like extra regiochemical interesting cases. Okay, so I'm going to just put them in this box here. I'm going to put a couple of them, and I won't solve them just yet, just because of time's sake. But I'll put it at the end. Probably I'll go over them really quickly. Go ahead and solve these problems. You can use any nucleophile you want to. Just don't use concentrated, because concentrated is just not going to, I mean, it'll work for this one. So you can do either one if you want to do concentrated as well. But for these other two, these other ones, make sure that you do them with some nucleophile. They're not going to make sense if you do it concentrated. Go ahead and try solving these problems. And then there's one more for this one. I'll have to fit in somehow. I'll just make more space at the bottom here. So the blue box will be synonymous with some new problems that we can try out. Okay. Apologize if these are looking really bad, hard to read. I'll tell you this, these problems, the point of them is to make sure that you guys are conceptually up to check with the idea of regiochemistry. That's really what these problems are doing. So if you find yourself making regiochemical arguments for why one product exists over the other, you are doing the correct thing. Actually, you know what I'll do is this. So pause here if you want to and try these out. What I'm going to do is I'm just going to highlight where the regiochemical portion is, and it's your job to go figure out why that's the case. So I'm pointing at all the spots that are regiochemical. Go figure out why those are the regiochemical spots for the cation. This is clearly just an example of this, just like triangle to square. I think triangle to square is a lot more easier to visualize, so it's easier for you guys to make that change. But go ahead and try it out. Cool. So one more thing that we have to talk about with these acid mechanisms before we can move on, and this is everyone's worst part. I hate it too, but we have to talk about it. One thing that's really important to notice here is that we've been only really creating one stereocenter in all of these reactions. So this was only one stereocenter, this was one stereocenter, and this was one stereocenter. So all we had to worry about was if it's, R and S, right? We noticed that most times we would form both R and S. I don't know why I put R and R there. I apologize. But there is something interesting to be said about when we form two centers, because recall that both carbons of the alkene can react, so both carbons should be able to make stereocenters. Now, a way to do this with a disub is instead of using H+, what we use is D+. D+ is just heavier proton. It's just H2, right? H+ is just H1. So this is D+, right? It's just H. It's just a proton, so don't freak out when you see it. But the only reason why we use it is because when we add in D+, right, that's different from hydrogen. So if I have a deuterium here and a hydrogen here, those are different. And that means that can lead to stereochemical, differences, right? Because if D is not H, they're not the same group. We can have chiral centers borning from adding, hydrogens. So I'll try to use different colors here so we can kind of, again, notice things a little better. But I will use red for deuterium, and I'll use blue here for, the heavy water here. D2O is just H2O, but heavier, right? So deuterium, let's say it adds to, this carbon here. Again, doesn't matter. Either carbon could have worked. They're both the same. But let's say that it just added that one there. The deuterium can add, okay, either top or bottom. So that's what I'm trying to show here. Okay. And then what we get is a empty orbital on the side here that water can react with. Okay. The idea here is that water can add in one of two ways, right? Water can either add above or below. So let's say it attacks above here. That would mean that we're making this here and this here. Or water could attack from below. So above or below, right? So we did the above attack. This is the below attack. The same thing is true on this guy here. So I won't draw out everything, but it's the same thing. Actually, I guess I will. Water can attack here, or it can attack here. Okay, either one is possible. So let's do the above attack. Oops. Oh, actually, let's do this one as the below attack, and we'll see. You'll see in a second why I want to do it that way. Just makes things nicer. There's more of a congruence with the products if I do that. Cool. So either both the D and the OD end up on the same side in these cases, or they end up on opposite sides. We actually have terms for these, right? For these kind of additions where the added components are adding on the same side or opposite side. We call these syn when they're same side, and anti when they're opposite side. Okay, anti when they're opposite. So syn alkenes, or sorry, not syn alkenes, sorry, syn additions or anti additions. And for all the reactions we talk about today, we are going to have to consider whether our reaction is syn or anti. Okay. Now, if we look here, we can actually begin the conversation with just this disub-alkene. But looking here, what we can consider is, hey, when water adds, right? So when deuterium adds, we can't really control anything. Deuterium is just going to add one way or the other. It's going to add either from the top or the bottom. That's why we considered these two here, right? But when water adds, it could potentially be influenced. What could it be influenced by? Let's say we consider this hydrogen here. When water is attacking this orbital, does either deuterium or hydrogen maybe interact or influence the addition of this water? Well, because these are just hydrogens, these are really, really small, right? It's not very likely that water will do anything. We'll have an reaction with them that'll influence the addition. So for some reactions, we are going to see an influence, but with this one, we don't see very much happening. So disub, trisub, alkenes, it doesn't really matter whether the water approaches from either side. Either one is possible. So what this means then is that for acid additions of nucleophiles, it's very much likely that you'll get both a syn and anti addition. So we will get all four of these products if we did this reaction. The fact that there is no preference for syn or anti means that this reaction isn't selective or it isn't stereoselective. So this reaction is not stereoselective, it is non-stereoselective because we do not prefer syn or anti-attack. And again, this is the case for mono, di, and trisub alkenes. Majority of alkenes, you will never see a preference for acid mechanisms for syn or anti. So let's hope that we don't make two centers, because if we do, we've got to draw all four of these, and that kind of sucks. Okay. But something happens when we do the reaction with tetrasub. So tetrasub is going to be a little different. Okay. If it wasn't already obvious when I mentioned that only mono, di, and tri have this, sort of idea, but something's going to happen if I do this reaction with tetrasub. Use the same color scheme. Once again, I wish there was like a copy and paste function. It seems like there isn't. So I think I'm going to spend, if you have to skip forward, I'm going to spend like the next 2 or 3 minutes just drawing out the structures so that I don't have to draw and talk, because I hate to do that. All right, so hopefully you don't have to wait too long, and actually I'll put your stop if you're skipping forward, stop here. Okay, cool. So again, same idea. Proton can add either top or bottom. Both carbons are the same, so I'm just going to choose to do the right one here, just for the sake of clarity. But again, right, when deuterium adds, it can either add top or bottom, and what we get is a structure here. Now, before we asked ourselves the question, when water adds, right, how might the substrate influence or direct an attack on some side, right? So how might water be directed either top or bottom? Now, if we sort of take the same argument that we did before, or we try to take the same scenario where, remember how I said we looked at deuterium and hydrogen and we think about how those might interact, you might remember deuterium or hydrogen, not much of a issue. But methyl is a bit different because methyl is not as small as a hydrogen. Deuterium and hydrogen are both hydrogens, right? But those guys are not nearly as large as a methyl. And a methyl, if you think about it, is a CH3. So I'm gonna go ahead and draw atoms here. So how might this CH3 affect addition of that water? Let's focus on this bottom one here, just because I think it's easier to think about. But how might this water be affected? Well, again, CH3, big bulky thing, hydrophobic also, right? So water really doesn't want to interact with it. When water is approaching the molecule, let's say it's trying to approach from the top here for this example, it's going to start to interfere sterically with the methyl. So one, it really doesn't want to be next to this methyl. Two, it's also very big and it's blocking the way. So water is having a hard time interacting with that top side. Whereas if water just attacks from the bottom away from that, that methyl, it has an easier bit of time accessing that orbital. I think of it as like, the methyl is sort of like a propeller, or it's like a helicopter blade, right? If you were entering a helicopter, you wouldn't enter the helicopter through, like, let's say this is the door to the helicopter. You wouldn't enter the helicopter through the propeller. You would be dead. You would want to enter away from it, right? Like on the other side of it. So that's the same thing here. Water doesn't want to enter the club through the propeller. It wants to enter the club, the other way of the propeller. If that makes sense. And so water has an easier time adding opposite to the methyl. Well, another way of saying this then is that water adds syn most of the time as opposed to anti, right? So it adds syn to the deuterium, but anti to this methyl because it hates this methyl. It doesn't hate it, but it's a bit of an issue. But we're more likely to see syn additions than we are to see your anti. Why am I giving them colors? It's because I was just gonna write stereoselective here in one of the colors, but this reaction is now very much stereoselective. I think I'll do this actually. This reaction is very much stereoselective, and it is stereoselective for the syn isomer, where O, D, and D add on the same side, as opposed to the anti. So we are more likely to get syn addition than we are to get anti addition. I think the value that you probably get in the book or something is like 60% for this racemic mixture. So that leaves about 40% for this one. So this one gets 40%. Which again, that seems like nothing. Actually, yeah, let's make it a little more significant. I don't think it's, what is it actually? Should I check? So I know it feels like I'm adulterating numbers here, and I guess I kind of am, but I do vaguely remember this wasn't 40, it was about 20%. But I don't think that this was 80. I think it was more like 60. Regardless, I know it was a large difference. I know for sure this one was 20. So I'll go with this. Just fact check me in the textbook or something if you need to. But again, clearly there is a difference here. This is not very much close to each other. We're going to have a stereoselectivity, right? We have a bias for one kind of addition over the other. And in this case, this is very much true for tetrasub. Cool. So if we're doing reactions, acid mechanism reactions, we shouldn't really care about the the stereoselectivity for most of these guys. I'll tell you what, most professors with monodi and tri, what they're going to do is use hydrogen, because if you just use hydrogen, as we saw with these examples here, only one chiral center really ever tends to form, and it really saves your life when that's the case, right? So they try to make it so that only one chiral center forms, but if they do make twos form, it's going to be with the tetrasub. And that's where you need to remember, syn addition is more likely to occur with a tetra than it is with any other one. Cool. So this idea we'll come back to with every reaction. Again, I know it's not everyone's favorite. It's definitely not my favorite, but it is something we still need to consider because it's important, right? It dictates a lot of reactivity in our system. So again, come back to this for every single reaction. Some will be easier to, I think the other ones will be a lot easier to explain than these, okay? Cool. Well, congratulations. We have now completed the first set of reactions. These reactions concerning the acid additions of nucleophiles, right? Or the cationic additions of nucleophiles, really, right? So in all of these cases, whether it be with water, alcohol, I'll just put one halide here. Water, alcohol, or let's say Cl, right? We will form, oh, not that. We will form these substrates, right? These products. And again, all of these are going through that most stable cation that can form. So when we think of acid, we should really think about where is our cation most stable. I guess we also talked about isomerization too, which is good to think about because again, that is another example of going towards high stability or a lot of stability, right? Most stability possible. Okay. So with these simple systems where on the pi bond, we can form the most stable thing, we will, right? And we'll be happy when we do that. But remember, we still had those other systems where most stable was not necessarily on the pi bond. So for example, this system here, where most stable was actually on the neighboring tertiary, right? So we could form with acid, unfortunately, if we want to do this reaction, or maybe not unfortunately just quite yet, but if it is reaction with acid, our most stable, center was actually one downstream a little bit, right? It's the next door carbon. That's where our cation is the most stable. So what if I wanted to control my reactions onto just the pi bond carbons, right? In industry, when we have an alkene, it's never really the aim in industry to actually react past the alkene. If I form an alkene in a synthesis, like in the lab, I want to react one of these, both of these carbons. That's where I want to keep my functionality. So what if the point of my reaction or form the alkene was to actually make, for example, this product here, right? The non-rearranged product. How can I do that? Well, I certainly can't use acid because acid forms cations and cations are going to rearrange. So fortunately, cations can't do this for me. Carbocations, I should say. Carbocations are not going to help. So acid's not really going to help me here. So how can I introduce a cation that will activate the alkene for attack, but limit it to only the pi bond carbons? Now, if we think about the cations in this class, there's carbocations, there are, I guess, protons as a cation, but there's one cation, right, that we need that's, not going to act like those two guys, right? Carbocations are going to rearrange and do really messy stuff. So this next section is going to concern these reactions that limit themselves to only the pi bond carbons. Okay, so I'll label them. We're going to limit ourselves to only the pi bond carbons, where we react with the more stable carbon, or the one that forms the more stable, intermediate, and does not rearrange at all. And so the first reaction that we concern ourselves actually uses a cation that we've seen all throughout 118A. We just never knew that we could use it. We're going to use a metal cation, which is kind of like, it's kind of cheeky, right? Because it's like, oh, metal, like that makes sense. We can use metals. Metals can store cations. And so we're going to go ahead and consider that. So because we're doing a new mechanism, let's use a new color here. This is known as oxymerc, demerc, or oxymercuration, demercuration, but I'm too lazy to actually write it out in full. And how does this reaction work? So I'm going to continue to use this substrate here because, again, if the point is to, to prove to you guys that it won't rearrange, we might as well use the one that, the substrate that tends to rearrange an acid. Okay, cool. So how does this reaction work? Oxymerc demerc, as the name kind of suggests, uses a mercury reagent, specifically this one here. This is mercuric acetate. Acetate is this group here. So this carbonyl with an oxygen next door is known as an acetate. And that's, when we refer to it, that's what we're calling it. It's an ester of sorts. If you remember that term, it's an ester. Okay. So how does this reaction proceed? Well, again, if we're doing electrophilic additions, there must be some kind of electrophile. And again, metals are great electrophiles, they're great cations. So we can go ahead and have our pi bond attack this mercury. But if we only do that one attack, like we talked about, if we do one attack, we're probably going to form this cation again. And that's an issue because that cation is going to rearrange, right? Even in cases where, we don't, even in cases where, we have powerful nucleophiles, it's still a 50-50. So, I want 100% no rearrangement, right? So I've got to do something else. Well, remember how we proposed that one structure, right? That one thing that, we knew couldn't work for a proton because protons have only one orbital. The idea here is that when Mercury gets attacked by the pi bond, Mercury actually attacks back. So it actually forms two bonds to the alkene, to the alkene. And when it does that, it actually decomposes off or it kind of kicks off one of these guys as a leaving group. The way it does that is like this. So I know that you guys are probably gonna learn this arrow here and call it a day, but trust me, it's gonna be better for you guys if you learn to do it this way. You will thank me very soon for teaching you guys to do it this way. But this is how we're gonna show this group falling off. That's just gonna fall off as O- like this. So just gonna be hanging out, out in the world. But one of the acetate groups falls off, the other one stays on. This is a common abbreviation of acetate, by the way. So these are identical to each other. So I'll leave it up there. But what we form is this ring here. Now, if mercury is neutral with two bonds, that means it's going to be a cation with three. And now we have formed our mercurium ring. So look at that. We have formed a cation, but it is not a carbocation. And because it's not a carbocation, it is not going to rearrange, which is amazing, right? Mercury, I mean, metals probably do rearrange somehow in real life, but that's like inorganics, thing to deal with. Our thing to deal with is just the fact that mercury is not going to rearrange. So great, we're happy. So what do we do now, right? How do we understand this, right? What are we supposed to do with this? Well, luckily for us, we actually do already understand how to work with this because this triangle here is not, it's not new to us. We actually have seen this triangle before. Okay, so I'm going to redraw this triangle here just a little bit simpler. And I'm just going to just put plus there to signify that it's this form here. But this triangle we've seen before. We've seen a heteroatom, a non-carbon atom positively charged in a three-membered ring before. What is that? What is that ring, right? What is that atom? Don't think too hard. This was literally right at the end of 118A. This is an epoxide. Not only just any epoxide, an epoxide that's protonated has the same charge state as this mercury. So if we think back to how epoxides worked in acid, right? We should understand then how mercuries work in these reactions. So, take a couple seconds, think about it. It's not, don't think too hard. Again, it's a 50-50, just choose one, right? You're either right or you're wrong. But in acid, recall that epoxides had high carbocation character, which means that they follow SN1E1 mechanics. Interesting, right? SN1E1 mechanics showing up once again. So all that cationic stuff we were thinking about earlier applies now as well. Okay, so we have this cation here, and that's the side that a nucleophile will attack. So more sub-attack by the nucleophile happens in acidic media for epoxides. So what do we think is going to be the case for mercuriums? It's not a trick question. It's exactly the same chemistry. So look at that. Back in 118A, you actually already learned how to do an alkene reaction. You just have to learn the epoxide reactions first. And one thing I want to make sure is that I know that this is the acidic condition for an epoxide. I'm not saying that mercurium is an acidic condition, not at all. I'm just saying that it mimics an acidic condition, right? But it's not in any sense acidic. If anything, it's slightly basic because it has acetate floating around there, okay? So every year people get confused by that. I'm just drawing an analogy to acidic condition. This is by no means an acidic condition. It just has the same, reaction as an acidic condition. Anyways, if that's the case, then water should attack on that more subcarbon. And as a result, we get an alcohol, which will initially be OH2+, right? That's inevitable. Oh, I forgot to use colors. My bad, guys. Colors coming right up. Or maybe not, if you guys don't like it. I guess I don't know yet until after this. But what we get is the following. Okay, and alcohol in the making, and this mercuric acetate component here. Now I'm going to be a little bit lazy here. I know that this should be OH2 plus, but let's just say that a proton transfer happened, just to save a little bit of space and time. But remember, on an exam, mechanistically, you have to show the proton transfer. But when water adds on, it'll add on as such. And now we formed our alcohol. So this is a hydration mechanism, but it is specifically a hydration with no possible rearrangements, as we can see. Okay, that cation protected by the mercury. How do we get rid of that, HgAOC? Very, very simple. Just use a reducing agent. Sodium borohydride and methanol will do it. This is actually a really complex radical mechanism. And so what that really just teaches you that if it's a radical, just don't worry about it too much. It's going to be crazy, but it is going to deliver a hydrogen here radically. And what we get then is our alcohol product as such. Cool. So look at that. Now we can form products that don't rearrange, even if they have the possibility of rearranging. Okay. I think I'll use this whole top part. Say this is the mechanism box. Okay. So even if they could possibly rearrange, they won't. So I will go ahead and draw and redraw this over here. So you can kind of see it more in the how we would see it on paper. But typically what you see is mercuric acetate and water. Again, I will draw the intermediates just because it's good to see them. I will be using that Hg plus notation for the rest of this page just to save on space. But I do mean this here, right? I'm just not drawing it in. So please draw it in for yourself if you have to. I'm just being lazy and trying to save time. So I guess I'll do this because H2O is present typically in the same step as the mercurium. I'll put this as this is the intermediate, right? And again, if we think regiochemically, there is a difference between the carbons and we will not see a rearrangement. Okay, water will open up on this side here. Actually, I guess I'll do this. So I'll show the intermediate, but we'll show the product too. This is how you typically see the setup for this reaction. It looks something like this. And what we get is this problem here. Now, once again, if we look at this, this is a chiral product, right? This could be wedged or dashed, this water. And so the best way to kind of understand how this would work is to remember that the remembered rings can form above the plane or they can form below the plane. And water, when it attacks, is going to attack in an SN2 fashion. So this is where things get a little interesting, right? Because it's like SN1 mechanics in that this carbon here has the higher delta positive, right? But SN2 in the sense that it mimics an SN2 attack. And so what we get is, so in this case, water has to attack from the back. In this case, water has to attack from the front. So look at that, we're racemizing once again. It's racemic. There really is no preference for a side to attack as we've seen before. If we form one chiral center, really the only one we'd have to worry about. You can also apply this to the one with the tert butyl here. So I guess that's the one I'll put here since we did the isopropyl one here. But again, no rearrangement, so nothing to worry about. Nothing to worry about whatsoever. Now, we don't always need regiochemistry, right? As we've learned quite a bit now. We just need, an intermediate to work with. So we can totally have this butene here where, let's say we have the up wedged, we'll have the down dashed. And water could really open up any of these, right? There is no, again, there's really no preference for which one water opens up. Like which side it opens up, sorry, is what I should really be saying there. So in terms of like, we can choose either one. Thankfully for us, this is symmetrical. So if I open up on the left or the right, shouldn't really matter, right? Opening up on the left or the right, doesn't matter. I'm gonna get this product here. Opening up here on the left, let's say, will give us this here, right? Nothing really lost in translation here. So we'll make a racemic mixture. Now I know a couple are going to think, oh, wait a minute, but isn't this different? Like if I form this, isn't this different from this one? Yeah, those are different, but these two are the same. Those are exactly identical. Wait, are they? Oh no, they're not. I'm actually wrong about that. Hold up. Let me see this is how you know stereochemistry is for nerds. It's if I get it wrong. It's like even I don't know my stereochemistry as well as I wish I did. Okay. Okay, this was right. Let me draw the other one. So let's say that it opened up here. Which one is this? Oh yeah, these are the same. Yeah, sorry, these are the same. That's what I thought. But anyways, either of these are possible. It just forms a racemic mixture. Once again, we do have the possibility of doing that, you know, one example where we have this here. Again, I'm gonna save a little bit of time here. I'm not gonna draw out the intermediates. Actually, I guess I could. You know, I always say that I'm not gonna do it and then end up doing it because I realize it's probably just more important to just do it. It takes a extra second anyways. But now, right, if we open up, this is where it gets a little bit annoying because we can get a lot of products here. But if we get, let's say, on attack on the right side, which is different, lucky for us, we only get this product here. But attack on the left or the right, sorry, attack on the left will result in two different isomers. Again, racemic for these guys. So a bunch of the same stuff we're seeing is occurring here. I mean, if you wanted to think about it, you know, with analogy, pretty much we're doing the same acid mechanism. We're just not rearranging. So everything we saw with acid is happening here. It's just rearrangement's not going on. So that's a good way to think of this reaction is it's simply the non-rearranging acid mechanism. I hope I labeled this right. Okay. And so this is what we can get. Now, we don't actually only have to do this reaction with water. As we saw, if water works, then we should try organic water. Organic water is just alcohol. So let's say I did this reaction with methanol. This would react, just put a OM here, or you can just put a methyl sticking out just like that. And that would be our answer. So just like with epoxides, as long as we have an electron source, some kind of nucleophile, right? As long as we have some kind of nucleophile, these reactions should work. Sorry, this should be S. This should be R. Yeah. As long as we have some kind of nucleophile in solution, right? Any source of electrons, really, this reaction should work. So consider then the following problem. Let's do this actually. 2, 3, 4. Okay. So consider then the following problem. Let's say I took these reagents here and I did this reaction. So I added water in. I'll do you guys a little bit of favor here. We'll go ahead and draw in the mercurium. You can draw whatever stereochemistry you want. I don't really care. As long as you remember, again, this is just going to racemize at the end anyways. Let's say we had this. Here's what I'll push you. What's going to happen? What's going to happen next? So pause and take a second to think about this if you have to. So this problem here is going to require that you remember what I was saying like a couple seconds ago. As long as there is a source of electrons, the epoxide, or sorry, the mercurium ring will open. So why was I saying that? Well, water, when it reacts, what it's really reacting as is an oxygen source, right? Where alcohol, when it reacts, it's acting as just a nucleophilic oxygen source, right? So long as oxygen is there with electrons, it'll attack the cycle. So what about then this alcohol here, right? I mean, that's an oxygen with electrons. So can this oxygen open the ring? So then maybe answer yourself that question. Think about that for a couple seconds, right? If either of these oxygens can attack, right, because they're both oxygen sources with electrons, which one is the one that's going to open the ring? In this case, the intramolecular, or the alcohol in the same molecule, is going to be way faster than the water molecule, because intramolecular processes, if one molecule just needs to react with itself, right, that's faster than two molecules need to react with each other. So again, as long as there is an electron source, we can break open this ring. We don't need it to specifically be a different nucleophilic water or different nucleophilic alcohol. As long as on the same molecule, there is a reasonable nucleophile. So in this case, to help you guys out, the way that I like to do this is I count the oxygen 1 attacks carbon 2, and then every carbon in between. So 3 and 4. Oh, this example, it's not going to work, actually. Oops, hopefully this didn't confuse anyone. I have to modify this a little bit. Let's modify it like that. Sorry. Apologize to anyone who got stuck on this problem. So actually, we can still consider this. This is a 4-membered ring. 4-membered rings are strained. That's probably not going to form. So instead, we can consider the 5-membered ring formation. Now, actually, I'll make sure it's regio. I should have made sure. Yeah, for sure it's an attack here on the 5, because now not only is it 5-member, but it's also more substituted. Definitely going to attack here. So I apologize for that. But we form a 5-membered ring where oxygen is part of that ring. And so one way to remember this is oxygen 1, if we label on here, so 1, 2, 3, 4, and 5. Oxygen 1 attacks carbon 2, and carbon 2 has 2 methyls sticking out. So there should be 2 methyls here. Okay. Carbon 3, 4, and 5 are all going to be kind of boring. Carbon 3, though, is going to have the mercury on it. Okay, so carbon 3 has the mercury on it. Okay. And so this is now a way for us to make cyclic ethers, because after we reduce with methanol and sodium borohydride, what I get out is this cyclic ether. Okay. So cyclic ethers, remember, that was something we learned back in 118A. We did that with Williamson ether, right? Like if I had a bromide and an alcohol in the same molecule and I deprotonate the alcohol, this guy could swoop over and attack. Same idea. It's just that we don't need to deprotonate our alcohols in mercuric acetate mechanism. Now, another thing that you kind of might think here is, well, if the only thing I had to do was activate the alkene, right, like make it electrophilic somehow and react this, then technically this reaction should also work in acid, right? Because acid would just make the cation, and then the alcohol could swoop over and react. And that is true. Acid could also do this reaction. It's just that, remember, acid can also rearrange and do all this weird stuff that we don't want it to do. So imagine if like our substrate looked like this. Imagine if the cation formed here and there was a tertiary center down there, right? Like the pi bond was here and form this. This cation can rearrange and go to the tertiary and become a little out of sight for the alcohol, or sometimes maybe the alcohol can capture it. It's just a little complicated to do these reactions with acid. So to get exactly what we want, what we do is do these reactions with mercurium. So cyclic ethers is purely a mercurium kind of deal. We only really do this if you want to make, we only really do this with mercurium if we want to make a cyclic ether. Okay, cool. So another way to make this, and if you ever see this in synthesis, right, this sort of cyclic ether form, whether it's 6-member or 5-member, and you start from alkene, a very good way of doing this, these reactions, it's with, this alcohol over here. I like to think of these like alcohols as like nucleophilic arms, right, on a substrate, because it's just it's an arm that's like waiting to reach over and attack the pi bond once the pi bond is activated. Nucleophilic arms can be a lot of things. Like it could have been an amine or a sulfur, but in oxymeric demeric, we're really going to be concerned with oxygen nucleophiles. So don't worry about this reaction too much with other guys, although we can see like other nucleophiles or another nucleophilic arms reacting with other types of cycles. But this is typically oxygen nucleophiles. And again, it's a hydration with no rearrangement. By the way, I apologize for my handwriting. I know it's really bad. I'm just, I try to orate everything. I say everything really, really clear so that you know what I'm saying as I write it, so you know what to do. Cool. Anyways, nucleophilic arms, really cool stuff there. Okay. One last example that I can think of that we can look at is, so we talked about regiochemistry not being a big deal, right? Like it shouldn't really matter whether you attack on the left or the right here. And we saw that we made both products anyways. In this case, only one product for the right side, two for the left side. But one thing that we can, one problem we can look at that might have a regiochemistry is this substrate here. Okay, so why is this substrate important? Well, if I were to add the mercurium to it, and I'm only going to add it to one side, just for the sake of time and space, but take like maybe a minute and think about how, like, for example, let's say an ethanol this time, because we haven't been using alcohol examples a lot. Let's say an ethanol were meant to open this ring. How would ethanol react with this? Might it react a particular way? So just think about this for a second. So hopefully you guys aren't thinking too hard or going too crazy with this. This is very, very simple. So if we thought about the cationic arguments we've been making before for like epoxides, right? You might think about that first. Both of these are secondary though. So technically there should be no regiochemistry, but in fact, there is going to be a regiochemistry. And it kind of goes back to the idea that we're looking at here, right? Like technically both of these carbons are the same regiochemically, but the reason why we see a difference was because of that methyl that was kind of acting as a propeller, right? Preventing attack. Well, if we kind of apply that same idea here, we do have a methyl here that can act as a propeller and prevent attack, but we also have a tert-butyl. And a tert-butyl is 3 of these propellers. I'm gonna just draw big circles here. 3 of these propellers. And so imagine you're playing soccer and you're trying to make trying to kick a ball in the goal. That's all I know about soccer is kicking a ball into a goal. And instead of having one goalie there's 3 of them. Probably going to feel a little bit bullied, right? Like, what the heck? Why is there 3 of them? And that's exactly how ethanol is going to feel here. Because when ethanol wants to attack, it's going to see 3 goalies, right, on its way to this carbon and be like, oh, well, no way. I'm not dealing with this. This is cheating. And instead of, trying to make this work, it's just going to attack on the other side here. So this here is what I like to call inherent. I like to call this inherent stereochemistry, or sorry, regiochemistry, because it is not exactly clear immediately why this product only opens up on the left side. Kind of have to think about, the approach of the molecule as well. Okay, try to, again, just formatting a little bit here, just try to move some stuff. Okay, cool. So these are sort of the core concept problems. Kind of think about them. Again, one way that I like to think about these that I like using is the idea that this is basically just acid mechanism, but with no rearrangement. So most of like the answers here are about the same. The only one that would kind of differ in that sense is this one here, because acid mechanism, if it did react, and let's say it did react, how do I put this? Proton is not going to be hindered by whether there is a tert-butyl or a methyl. So this is the one example where it's not going to be quite the same as the acid mechanism, but pretty much most of these are, right? It's just acid mechanism with no rearrangement. Cool. So again, unfortunately, we have to talk about stereochemistry. I know, not the best thing in the world. I'm going to revisit cyclohexene. It's our best friend in this. But cyclohexene, when we react with HgAOC, T2, again, we can form the upwards face or the downwards faced. Cycle. And like we kind of mentioned before, right, these cycles are opened up on the opposite face by whatever nucleophile. So we'll just use water for now. Water is good enough. Okay. And so in this case, right, we're going to get like this. Just like that. Oh, sorry, not like that. What we're going to get is water adding on this side, opposite, and for this guy on this side, opposite. I guess I could have added in colors for this. So I'll do that as I talk. So how we do these reactions, very similar to epoxides, very, very similar to epoxides actually. And just like with epoxide openings, look at the opening. So while I'm drawing in these colors, right, just look at the openings real quick. Like what kind of descriptive stereoselective term would you use for these openings? Since the alcohol and the mercuric acetate are on opposite sides of each other, I think I would use the term anti. So it appears to us currently that there is a strong anti-stereoselectivity to this reaction, right? And that's always great because it's like, hey, we are seeing a clear relationship here. This probably makes a lot more sense than the first stereochemical reaction that we looked at, right? Which was the tetrasub acid additions. All right, but here's where things get a little bit tricky. And it's why it's always good to remember that, you know, some things are just out of our control. So it's just best to know them. But recall that I mentioned that the NABH4 step, the sodium borohydride step, that is a radical mechanism. Meaning that it's very likely that the intermediate that we go through for these reactions is a radical intermediate. And radicals are flat. So why is it important that radicals are flat? Because how H is going to add will depend on its approach of attack. So I'm going to, once again, take a couple minutes here to draw, skip forward if you have to. So I'm gonna put stop here in case you guys are skipping forward a lot. I know I'm not done drawing yet, but you know, I didn't want to sit in silence for too long. You can kind of get an idea though as to what what I'm getting to by all this stuff that I'm drawing. But because this is a radical mechanism, which kind of ruins our life a little bit, right? Water, or sorry, not water, but you know, the hydride or the hydrogen that adds in this radical method, we don't really know if it's adding the same side or opposite. We don't actually really know. So when hydride reacts, it can react this way, or it can react this way, right? It can react this way, or it can react this way. We don't actually really know. It'll do either one. We can't really control for it. So unfortunately, even though this reaction gives off anti so bad, like it feels so correct that it's going to be anti. Actually, let's use deuterium so we can, like, it makes two chiral centers. Let's use deuterium. Yeah. So remember, deuterium is just heavier. Doesn't matter. But we can have either a top attack or a bottom attack. We can't control it. which means that we form all 4 possible isomers here. And this reaction is non-stereoselective. So what was the color that we used before? We used orange. So we use orange again. Non-stereo. Selective. Oh no, boo-hoo, everyone's sad. I'm a little bit sad. Right? Non-stereoselective process, what are we gonna do? It's okay. Like I mentioned, with these kind of problems, professors do their best to make sure that, you know, you get problems that don't force you to draw 4 things. They try their hardest. You'll probably have additions where you only form 1 chiral center because of this. Because again, you know, these are not the cool reactions we want to do. Whenever we want to form 2 chiral centers, we want to do it with reactions that have a very specific anti or syn selectivity. We don't really try to do, you know, no one's really trying to see if you understand that a reaction can make so many different products. At least I can only hope and pray that that's the case. Okay, so all hope and pray that's the case. Why is it doing that? Oh, that's why. So syn, anti, syn, and anti. I know what you're thinking. You're probably thinking, well, would it matter if it's trisub? And the answer is actually no. It won't matter if it's trisub. The reason for that is because, you know, remember that the previous time that we considered, you know, oh, tetrasub, sorry, is what I meant. Would it matter if it's tetrasub? Because back here, tetrasub did turn non-stereoselectivity to selectivity. I'll draw it on here, right? Keep in mind that water, when it was attacking, water is a big thing itself. And so that's why there was a lot of sterics when it was approaching. But hydrogen is a very small little dart, right? It's a very small little dart, if you think about it. And it doesn't really have an issue if there's like a methyl. Like I can even draw it in if you want. But when hydrogen, this small dot, is trying to get in, it's not really going to be it's hard for it. It can actually like sort of sneak its way in. And some nucleophiles are actually designed with that purpose of being very sneaky and, you know, very able to enter like tightly governed spaces. One that comes to mind actually is N3. N3 is quite commonly, you know, deemed a dart. It's seen as like a dart in the industry. I know this is not a dart, but it looks like a dart because it's really planar, it's small. It can get into really tight spaces. So we use N3 if we can't get a nucleophile to work. But yeah, this is going to be non-stereoselective. If you have to do this reaction, you're drawing everything you possibly can, right? Also explains why we always, you know, tended to see racemics, right? If you're not already kind of seeing it, most reactions are going to be racemic of some kind or diastereomeric. They can also just be achiral, right? Like a couple of these back here were just achiral. There is one more type of mixture we can make, and we'll cover it with the next edition. So actually, yeah, we'll cover it with the next one. So let's go look at what other kind of mixture we can make. Okay, cool. Actually, I have one more problem that you guys can try out on your own. And it's actually a little play on this one. So 1, 2, 3, 4, 5. Okay. Okay. So go ahead and try this one out. Take a couple minutes on that. Do the reaction on this. Do whatever nucleophile you want. Doesn't really matter. Hopefully you can see why it doesn't matter, but do whatever you want. Hopefully you tried it out. If you didn't, it's okay. The main point to take away from this one is the fact that if you do an attack here, right, you can form a 5-member this way, or you can form a 6-member this way. And a great question is, well, 6 is better than 5, right? But 5 is more substituted. So what actually matters here? Well, when they did this experiment, right, they had the same questions, and it turns out, really cool enough, that we're actually going to make the 5-membered ring. 5-membered is way more popular in this case. So this is the 5-membered ring if you want to compare the answer. Okay, I can number everything if you'd like. 1, 2, 3, 4, 5. Okay, the 6-member ring doesn't form, and this is twofold. One is the point that because we're going through an epoxide intermediate, 5 and 6 are both pretty good. So we go with the one that fits our model the most, which is attack on the most subside. The other reason is actually back in 118A, we taught you guys very briefly that 3-membered rings form faster than 5-membered rings, which form faster than 6-membered, forms faster than 4-membered. So we actually told you a long time ago that 5 is better than, like, faster than 6. So that's another thing that helps govern this, this formation. Cool. All right. As always, we're doing these reactions in chunks that make sense, or in chunks that are related. So you can imagine the next 2 reactions are going to be related to this. And so all of these problems we're seeing here are also therefore then going to be related. Okay. So the next reaction is going to be the reaction with X2. So Br2, I'll put it here like Cl, Br, and I. Okay. And so how does this reaction work? Well, we don't really have a metal, but we do have halogens. So how do halogens, in their elemental form react with pi bonds? Looking at this, there's really no charges, right? But we know that alkenes have to be anionic, right, to some extent, and that therefore then this reagent has to be electrophilic. But halides we consider pretty electronegative, or like those guys tend to have electron density, at least compared to a carbon. So how in the world are we going to force a minus charge, or sorry, a positive charge here? Well, the really cool thing is that when these two things are in space and really close to each other, again, alkenes are anionically charged. So when these electrons get close to the pi bond, or sorry, to the X2, the X2 bond actually polarizes because electrons don't want to be close to each other. They hate each other. And so the electrons actually move towards the other side. So in this pi bond, right, are electrons, and those electrons are influencing the electrons in this bond, this sigma bond here. So much so that we have a positive X and a negative X. We have this dipole form here. There is our electrophile. And what's going to happen is X is going to be attacked. Now, once again, right, if we form this X, we're going to form a cation here. We don't want that because cations rearrange and they do nasty stuff, right? And these 3 reactions that we're covering are meant to be non-rearranging. So what's going to happen? Same as before. X is going to attack back, and X is going to lose a leaving group. Would it surprise anyone that it's X? Hopefully not. Again, X is going to form a ring here. Okay, sorry about that. So again, X is going to attack, going to form complex again that we saw before, and it's going to lose a leaving group. And we yet again form a 3-membered ring with a cationically charged heteroatom. Any surprise there? Hopefully not. So if before, right, all we needed was a nucleophile to open up this ring, then shouldn't surprise anyone that that X minus that we shut off, which is also a pretty good nucleophile, is going to open up our ring. Now, where do we think it's going to open up the ring, right? Again, we have regiochemistry. Where are we going to open up that ring? I mean, if this is anything like the epoxide chemistry, anything like the mercurium chemistry, it is going to open up on 1. Totally going to open up on 1. And so what we form here then is going to be the dihalide. Okay, we call this a vicinal dihalide. They are neighboring carbons with a halogen, right? So we have this halide system here. So this is the halogenation reaction. Pretty cool reaction here. And again, what we get is that cyclic intermediate that just forces itself open and makes our life so much easier because it helps us understand reactions better. Now, one really, really important thing about the halogen reaction. So again, I'll redraw this here. Right, I'll even draw the intermediate. Really cool thing here is that we get for the first time a difunctionalization. So what do I mean when I say that? What do I mean when I say a difunctionalization? All of our reactions up until this point have been additions of H and some nucleophile. right? I mean, if we literally go back, H had to be added in the acid mechanisms, right? H had to be added in the acid mechanisms. And then this mercurium was just HOH. It was just a hydration mechanism, but no rearrangement. This, though, adds 2 halogens, which is 2 functionalities. The true power of the alkene is being realized here. And this is synthetically where we're really going to have a lot of fun, because if you have 2 functionalities, you have 2 chances to do a lot of things. And so great little thing there. As always, right, we do form a center there. And much like the last set of reactions, right, this center can be racemic. Okay. What would this be? This would be R and this would be S. So racemic once again. And why is that? I'll still draw it for you, even though we have it drawn on the other page. Actually, I'll draw it very quickly, but it's because, right, we can have a wedged cycle. We can have a dash cycle, right? It doesn't matter which one we form, as long as one of them forms, and we can open them up to give us the products seen here. I'll orient them though, so it's not confusing, right? Which one forms which, although we should know which one forms which, but just in case, I'll put them there just in case. And we form, right, a racemic product here. Okay. Once again, we can also react with, right, an alkene that doesn't have any regiochemistry associated to it. Form this here. And in this case, right, not only do we form 1 chiral center, but we form 2. And so normally we do this on the other page, but who cares? We can get a little, into it now, like get a little sneak peek of it. But if we are, let's say, opening with X, it doesn't really matter where X opens from. So we can get this X here or this one here. Or down here, we can get this here. Now, this example is meant to highlight sort of 2 ideas. One of them we'll talk about now, and the other one we'll talk about in a second on the other page. But one thing to notice here is that because we're adding 2 X's to both carbons, there's a really good question here. Do you guys think it actually matters how this ring had opened before? So we said that this opens up on the Mohr sub, but do you guys think that actually really matters? That's a good question to think about. Does it actually matter that this opening opens up on the side, that stabilizes the cation better? Does that actually matter? So take a little bit of time to think about that. Don't think about that too long. The answer is no. Even with regiochemistry, if we're adding 2 of the same things, right, to the double bond, why does it really matter which one adds, to the Mohr sub and which one adds to the less sub? Right? Or why does it matter that one adds to a stable cation and the other one didn't add to a stable cation? The reality of it is, sorry, let me just finish drawing this. I don't know why I was brain farting on these, but yeah. The reality is, regardless of how it added, even if I didn't know this mechanism, right, I could have not known this mechanism, I'm still getting 2 X's heading across the pi bond. So when these, I was thinking the word pioneers, but I think when the first scientists were doing this reaction, they weren't really sure immediately that, this was going through the cyclic intermediate. Now we know this because of subsequent experiments, but just from X2, you can't actually tell that this opened up from a ring. How do you know it didn't open up? How do you know it just didn't do this? How do we know X and X didn't just confluxate like that and just add on? I mean, we haven't seen it yet, but we'll see a reaction like this where all it does is confluxate like that. So how do we know it didn't do that? Well, again, we need a subsequent experiment that kind of helps us here. And that experiment is going to be the following. Br2 in water, or bromine water. So why is bromine water so significant? Well, recall, like we talked about on the last page, as long as we have, right, some nucleophilic source of electrons, right, anything can really open up these rings, right? If they exist. If this ring exists, then anything can really open it up, even another nucleophile. So yes, X minus is in solution, but we're also going to drown it out with H2O. So when we form the bromine ring, right, what we're hoping is that water will open it up. And if water opens it up, we get two possibilities, right? Either we get this one where water opens up on the less sub, or water opens up on the more sub, right? If this mechanism is the same as our previous mechanisms, it should open up on the more sub side, right? So we'll hope for that. But if it's not, then it'll open up on the less sub side, and we'll know to worry about that. Okay. So before we go into what's the answer, why does this work, right? Why is it that this water can even work? Isn't water a weaker nucleophile than bromine? The answer is yes. Br minus is a lot stronger than water. So there probably is a small population of product that is, the bromine opening up the ring. But more times than not, water ends up being the one that adds mostly. And why is that the case? Well, one thing is that, remember, bromine and water, that's going to cause a solvent shell. And solvent shells are meant to slow down the nucleophile that they're shelling and to make them less effective. So bromine on one hand is going to be less effective, right? Because it is solvent shelled in this product solvent. The other hand is that water is being treated as a solvent. So not only is there water, but there's a lot of water. We are quite literally drowning the bromine in water so that there's so much more water. You can think like 1 to a million, right? One bromine, one Br minus to a million H2Os. And the hope is that when the cycle forms, water will be the more readily available nucleophile. Okay, so this is how this reaction works. And if we see other nucleophiles, those are going to be the nucleophiles that open up. It's not going to be the other halogen. So be very careful with these kind of reactions. I'll show a couple more examples of this too. But when we do this, it turns out that yes, we do have the same exact mechanism, and water forms on the more substituted, more stable position. Okay, so we form this halohydrin here. It's called a halohydrin because halo for bromine, hydrin for the water. This is a halohydrin. Okay, so as long as we have another nucleophile, we'll open up the ring, and it'll open up very similar to all of our 3-membered ring openings. Like I promised, I will show you all the possible, or not all of them, but I'll show you a couple of them. But we'll definitely form a ring here. And then ethanol is going to act as our opener. Forms this here, right? So you guys can kind of see, you can get really good at just guessing, right? Let's say I had a trisub here, right? I mean, you can just kind of guess. I don't have to draw the intermediate, but you can kind of just guess, right? Let's say I did this in Br2 and thiol, right? Thiol is a nucleophile here, right? The nucleophile is going to drown out the bromine. In a sense, bromine is only acting as an electrophile, right? So bromine is going to be the electrophile here. Where does our nucleophile go? A nucleophile goes on the more sub, and our electrophile goes on the less sub. And these are both racemic because we're only really forming one center here. Oh, by the way, I don't know if I ever finished this, but we can clearly see that this is anti, like the previous reaction. So we can, think about this being an anti-opening. Okay, I guess I'll draw the intermediate. Okay, cool. So we have this here. Now, again, we should consider the two bonus examples that we did here, right? This guy and this guy. But, I'll leave it to you guys, right? Like, I don't think I really need to explain much here. I think you guys now have the ability to answer these on your own, but consider what would happen if I did, let's say, Br2 and it's another nucleophile, let's say NaCN, right? You can draw the intermediate if you like to. I mean, I'll draw it for you. But what would be the answer? You can also consider if we had this here and we just added Br2. Okay. And what would happen there? So I don't think I need to really answer these just quite yet. I think you guys can solve these pretty well now, just based off what you've learned. from the previous ones. Cool, cool. So as always, we need to talk about stereochemistry, but we already kind of have talked about stereochemistry. Luckily enough, we've figured that out for ourselves. A very important stereochemical consequence of this reaction is that it's anti. Okay, so let's go ahead and take this to the next page. We are forming anti-products. And so for just right now, I'll do the sort of generic, any nucleophile can be added sort of deal. But if there is no regiochemistry, which, is a bummer, but can happen, we will form a lot of products. Right, so let's say we're doing this in water, for example. What we will form is bromine and water like this. And bromine and water like this. If we do the same thing here, so the same idea, just opposite stereochemistry. One thing I want you guys to kind of notice here, though, that maybe you kind of notice it on the other page too. I just didn't mention it explicitly. Is you'll notice that a lot of these molecules sort of have interesting relationships to each other. Okay, so what I mean by that? Well, these guys here, right? These are just different openings, but look at this guy and this guy. What's the relationship between them? Right? This bromine, like the bromines match up, the alcohols match up. Let's just give these like, I'll just say, let's say this is R, this is S, right? That must mean that this is S, this is R. Same thing here, right? Alcohols match up, bromines match up, right? This is R, or that thing that's actually S, right? Yeah, this would be R, S, R, right? What do you guys notice about these guys? These guys are enantiomers. And so are these guys. They're also enantiomers. So in the case that you get, for example, a symmetrical alkene, or actually let's just say it this way, right? Let's just say that you get an alkene that is not regiochemically specific or regio-specific, right? You're basically forming two products, right? You're basically forming two products. You're forming the product where bromine shows up on one carbon and the alcohol and the nucleophile shows up on the other, and then the flip of that. And on top of that, you're just forming racemates of both. So both are racemic. That's it. That's all you're doing. So you can actually even simplify this. You don't have to actually draw all four out. You can if you want to, but you could just draw these two, right? Just the two like position switch, right? Like bromines sort of on the top carbon and bottom carbon, right? Until you notice something else too that I just realized just right now. If you look even closer, these two are the same. And these two are the same. Okay. It'll be a little, or is it the case? Sorry, wait, which ones are the same? No, yeah, wait. Oh, no. Sorry, that can't be true. These are the same. And these are the same. Okay, I apologize. I'm clearly very bad at this. I need to get better. So there's third activity. I will put a note that like in the description, like, I kind of did a little bad on here. Anyways, I'll be honest, I don't know why I can't tell which one is the same. I think this is correct now, but the point is that they're the same. So you really only form one racemate here. Okay. So for symmetrical alkenes, you're only really going to have one product that is racemic, right? That's just going to be the case. I think, the thing that I was getting confused with is when it's not symmetrical. So it's not symmetric. You can go ahead and do everything. But the point here is that you'll form this guy and this guy. This guy and this guy. And because these don't look the same, right? They're both going to form racemates, their own racemates. Again, you could go and do the whole thing. I don't want to because I hate stereochemistry. I'm not good at it either. But yeah, we're going to form two racemates in this case. So no regiochemistry, right? We get this, we get this. Now we can still form two stereocenters. And we can form two stereocenters on a trisub, but this is a lot easier because when there is a regiochemical difference, which we can see here, thankfully, right? We are going to get pretty much only one adduct, right? The nucleophile, which I'll change up this time. Let's make it, let's just make it water. It's fine. Water is fine for now. Let's make it simple. Water, remember, is always going to add on the more sub side, and bromine is then therefore going to be on the less sub side, right? This is going to be a racemic, so we form both of these. But again, right? Because water is always adding on one carbon over the other, we never really have to worry about the other case where OH is here and Br is here. We're only going to get this again. Very, very specific anti-selectivity, our very second reaction now that's anti, right? We had a syn reaction a long time ago, maybe 2 hours ago. Now we have an anti one. We had a pseudo anti just a second ago, but this is what we see here. Now there's one last portion here. I always hate talking about this. It always confuses people, but I will show it, right? If we look here, we have an anti-alkene upon which we did an anti-reaction. So a disub anti-alkene, if you do an anti-reaction on it, actually, let me put it this way. So anti-symmetric. So it's anti and it's symmetric. And we do a disub reaction on it. I know I drew 4 different products here, but I wanted you guys to maybe notice something. And it's okay if you didn't notice it. It's a hard thing to notice, but these are all actually meso. You can tell because let's say I focused in on, so I'm going to compile all these together now. Let's say I have just this one. A very good diagnostic that a molecule is meso is to look at all the like groups and see what their relationship is to each other. So what do I mean by that? So if we look at the X's, which are the like group, right? Those are anti. If we look at the H's, again, like group, let me use a different color actually. Those are also anti, like they're opposite of each other. So anti-H, anti-X. And if we look at the methyls, the like groups, they are also anti. When all 3 groups on 2 carbons you believe to be on a, when all groups are the same relationship from each other, right? On a molecule, that molecule will be meso, as long as the groups are identical, right? This is meso. Okay. Just make sure that all groups have the same relationship. A very, I guess, one way to remember this is that if you do an X2 reaction on a symmetrical anti-alkene, like disub anti-alkene, you're going to get this result. So this is unfortunate, sort of another stereochemical thing we have to kind of remember. In my opinion, just get the concepts right. Stereochemistry is like a couple points of every question anyways. And I really don't like stereochemistry. It's really convoluted and hard to think about. Cool. Anyways, X2 additions, pretty much the same as these guys, right? The water addition, the cycle additions, but we just have an extra nucleophile that can add on. Now to sort of just answer these, like this one here, the nucleophile adds on the left subside, right? Just like we saw last time. And this is going to be like racemic, right? For this one, bromine will form a cycle. There was 2 concepts in here. One is the concept that this nucleophile will attack. The other one is that it attacks to make the 5-membered. Now this 5-membered might have been a little difficult, but it's a sulfur, it's a thioheterocycle where we're going to have sulfur 1 attacks carbon 2, 3, 4, 5, 6. Oh, actually, it was not 2 concepts. I thought it was. It's not. The other concept would have been that 5 versus 6 one, but it's okay. This is good enough too. 1, 2, 3, 4, 5, and 6. Where people have a hard time with this one is that carbon 2 has a carbon on it, and that carbon is going to have a bromine coming off. So this is one thing that people have a hard time seeing. So that's what that one's going to be. Cool. So that's what we're going to have for that there. All right. So hopefully you guys are still there with me. You're not, hopefully not too bored. I know these are not always the most exciting things to do. But let's go into the very last cyclic mechanism. So it would be not very fitting if we taught you guys these mechanisms that, you know, were the same as epoxides, and then we didn't show you how to make epoxides, right? Like it would be kind of ridiculous if all we did was tell you, oh yeah, we can make epoxides. Of course we can. And everything follows epoxides, but we don't show you how to make them. So this next reaction is going to be the epoxidation reaction. Okay, how do we epoxidate an alkene? We do that with MCPBA. Okay, MCPBA, for those of you curious, is a benzene ring. Put chlorine wherever you want. That just means that 2 carbons down is where you're going to put the other thing on the ring. But we have this guy here, and that's MCPBA. This here you might recognize from Gen Chem, that's a peroxide bond. So metachloroperoxybenzoic acid is what MCPBA is. All right, so how does this reaction work? Well, if we look at the peroxybenzoic acid, and I'll only put the part that really matters here. We have this where R is the benzene ring. And I want you guys to look at this, okay? So clearly, what we're going to do is we're going to form this epoxide here, right? That's the point of this reaction. That shouldn't surprise anyone, forming that epoxide. But it might not be super obvious how we do it initially. It's not super clear or clean here. That's okay, because we actually, you know, I'll give you guys a little bit of hint here, right? We're actually going to use this oxygen here as our, you know, epoxidating agent. Sorry, not oxidizing, epoxidating agent. So that means that this group here kind of has to do something, it has to fall off. Well, wait a minute. We have actually learned of a reaction that has this group here. Does anyone remember what it is? That was the mercuric acetate reaction. So when mercuric acetate reacts, remember, we said that we attack the mercury and then we decompose off the acetate as such. So if we were to just kind of follow these arrows because we weren't sure what to do, well, look at that. That makes sense. We take this oxygen and form a ring from it, so that's cool. And then how do we get rid of this? We decompose it off. So we put this bond here, and then this pi bond we tend to put here. But keep in mind that we have to kind of resolve this hydrogen. It's not just going to float in the air. So instead of putting the electrons on oxygen here, the electrons actually just grab the proton instead. So look at that. As long as you know your mercuric acetate mechanism, you know your epoxidation mechanism, and it's so much faster. Just one and done. Immediately, it's over. Okay. And the byproduct of this reaction is a carboxylic acid. So actually, let me put it this way. If we look at directly what the end product is, it looks like this. But if we flip that over, that is basically just a carboxylic acid, right? Nothing there. So cool. So this intermediate that we've been, you know, or this sort of structure that we've been drawing analogies to for the last 2 reactions, we can also make that too. And we can do all the reactions that we'd want to. Now with epoxides, it's a very good thing to just remember, right? Epoxides can react 2 different ways, right? We can react with acid, or we can react with base. And we can observe, you know, regiochemistry in this reaction. Well, actually, let me do this. I know what to do. Okay. Recall that with acid, whatever nucleophile you add, right, that nucleophile adds on the Mohr sub. We'll make this oxygen like that. Okay. And so the epoxide opens as such. And in base, we open on the left sub. So we get something like this. Okay. Hopefully nothing too novel. And if anything, it serves as just a reminder. Okay. Once again, epoxides, just like with halogenation, although it's not immediate, epoxides give us access to these difunctionalized substrates. And it's these difunctionalized substrates that are going to be the most important things, right? Synthetically, you're going to see the most amount of like messing around with these guys here. Okay. Now, one of these in particular that's important is going to be the water opening of epoxides. And the reason why this is important is because of the stereochemistry you're given. So let's say that we have this here, and we just open it up with water. It doesn't really matter, H plus H2O, right? This is going to be directly analogous to X2 reactions, right? In the sense that we will get this or this. Oh no, there is something going on here. You guys notice something, right? I think I do. I think I noticed that the OHs are anti. The H's are anti. And the methyls are anti. I think that this is meso, and it is. So that's why this is one reason why the water opening is important, because it's that same idea where if we're adding two things across the pi bond, sure, it doesn't matter regiochemically, but stereochemically it can if you're adding across an anti-symmetrical alkene. So I'll even draw here where this would have started from, so that you guys can remember this. If it's symmetrical and anti, and you're doing what is an anti-addition, because this is anti, this is what we're going to get. Okay, cool. Oh, these are racemic, by the way. You guys probably already knew that though. Cool. Now I don't want to spend too much time on this because epoxide reactions are stuff that you guys have already done. It's a matter of opening these things with nucleophiles. Sorry, been talking for a long time there. The only thing that I'll kind of remind you guys of is that if I were to, how do I approach this? I could just show you. I don't know how to approach this, but if we kind of go back here, one of these substrates is actually really important to epoxides. If you look very carefully, one of these is really important. I guess I didn't name all these. You can call this a halo ether. And a halothiol, I guess. This is either bromocyanide or cyanobromide. Cyanobromide sounds cooler. Okay, anyways, the halohydrin is important because halohydrins also themselves, if you were to make them. So let's kind of do this here. You can treat this with NaH. So let's say we did Br2H2O. Treating this with NaOH also gives you an epoxide. So this is sort of an alternative method to making epoxides. So the question then becomes then, which one is the better one, right? Which one is the one that I want to be using to do this? And the answer is, really doesn't matter. Both of these will work. Really, the time you would want to use this one, this alternative synth, is if your molecule cannot tolerate MCPBA. So this might seem really confusing. What I'm basically saying is that some molecules are sensitive to the acid you form or the peroxide itself. Actually, one of the two next reactions we learned involves peroxides. Actually, both of them actually involve peroxides. Peroxides are particularly nasty. So some molecules don't want them. So if you don't want to use a peroxide, you can use this scent here. For you guys, what that means then for pre-meds to try and take a course, it doesn't matter. For me, it would though, for someone who actually works in a lab. Okay, cool. So take some time, just do a couple practice problems, probably for the sake of time, because I'm realizing, oh my God, I think we just hit the 2-hour mark right now. For the sake of time, I'm not going to do any more the epoxides. But again, like just do a couple price problems from Lieben's course from last year, or just look a couple up. Just remind yourselves of certain things you can do. In the synth guide, we'll talk a lot more about some crazy things you want to do with the epoxides and the bromohydrins and stuff, or the bromide stuff, right? But not much right now. Cool. All right. So now we have covered. So this is a great place to take a second break if you haven't taken a first one, or if you haven't taken a first one, this is a great place to take a first break. But now we have successfully covered how do we make sure the nucleophile only adds across the pi bond, and then cool things that we can do, right? How can we then add two guys here, right? Because acid mechanism didn't really allow us to add more than one functionality, but now we can add two of them. And not only can we add two of them, but we can add two of them only across the pi bond. That's great. That's amazing, right? So I'll just put X here. We can add another A group here, right? That's pretty cool. So that's great. We can do cation mechanisms. We can do cyclic mechanisms, right? This goes through almost always a cyclic mechanism. So almost always we go through this cyclic mechanism here for this one. But then the question becomes, okay, so it seems like we're going on the carbon that stabilizes cations the most. And that's cool and all, but what if I wanted to make this product? Or I wanted to make this product, right? Carbons that are not exactly the most stable for cations, or whatever intermediate that we're using. Clearly, these are not the favored ones. Okay, these products can be formed, and we will form them. We just have to kind of trick the molecule. One way to think about this is a lot of our additions have been like, if we have a regiochemical difference, we've been adding a nucleophile, right, to the more sub and an electrophile to the less sub. Now, I don't like thinking about this as more sub, less sub, more so than I think about the more stable and the less stable, but you kind of get my point here, right? Even for these reactions here, we figured out, oh, okay, like if I do a bromo reaction, bromide is the electrophile that adds less sub, and any nucleophile like water, right, would add more sub. So nucleophiles like to add more sub, and electrophiles like to add less sub. So if I want to add like, an OH over here from, say, these molecules, or a chlorine, what I have to do is somehow trick the molecule into thinking that chlorine or bromine, chlorine or alcohol is an electrophile. Now, I'll tell you what, OH plus doesn't really exist, but we did kind of see electrophilic bromine, right? We kind of saw it there. So maybe this is a little more accessible, right? This addition. Oxygen is going to be a little bit harder. So we're going to have to introduce sort of a Trojan horse, like sort of someone that is not an alcohol, but it will masquerade as an alcohol and we'll turn it into it, right? That's primarily electrophile. And that's actually the addition we'll talk about first. So how do we get that less sub alcohol? This is going to be the hydrobromation oxidation reaction. Let's use a new color now. Let's use green. Hydroboration oxidation. Okay, so this is going to be, like I tell you, this is the oxygen one, so this is another hydration mechanism. Okay, so how does this one work? So this reaction is going to use a borane. Okay, this reaction uses a borane, as the name suggests, as a boration, so it's using borane. So why is it that we're using borane? Well, we kind of talked about it a second ago. We need to trick the molecule somehow into adding an electrophile that's really going to be an oxygen. So how can borane be an electrophile? Well, if we kind of remember our periodic table, CNOF, B and B over here, there's a couple trends that might help us out in this. One trend is the Z-up trend, which states that, the more we go to the right, the more protons we're adding, the more nuclear energy that, is released from like the atom. So there's more nuclear energy going to F. There's very little nuclear energy coming from boron. Okay. Another thing that this basically tells us then is that the size and the electronegativity of borane. So one thing is that the electronegativity of borane must be very low. And we already kind of knew that, right? Because we know that electronegativity also kind of goes in this direction. Okay, so electronegativity goes this way. So if borane doesn't have very many protons, right? And it's also not very electronegative, it's then probably going to be a very large atom. And that is the case. It is very, very large. Okay, because it doesn't have the power to pull in all of its electron cloud very close. Atomic radii is very, very large. So we use R there for atomic radii. So if borane is large, okay, so carbon, borane, right? If borane is large, like say compared to a carbon, these guys are going to have a lot of steric issues, because imagine, if there's like a lot of carbons somewhere, right? A lot of carbons are going to act very, very sterically with a large borane. We kind of already saw that with the methyl and water, right? And that syn addition back all the way back in the first hour, right? Not a very good thing if we have bad interactions between these guys. So borane, if it had to choose between which carbon it wanted to interact with, right, whether the secondary or the primary, right, probably chooses the primary, because again, steric interaction is at the lowest point here at the primary, and borane would be really happy there because it's so large. So sterically, borane likes to go to that electrophile spot. But that can't be the only reason, because imagine borane has some nucleophilic quality. If it has a nucleophilic quality, then we're kind of screwed, because then borane is going to, add in the nucleophilic position. So how might borane be electrophilic? Well, another thing to notice is that carbon, right, nitrogen and oxygen, we'll do carbon and nitrogen. That's good enough, just for the sake of time, or carbon and oxygen, right? Carbon and oxygen have, different valencies. Carbon has 4, nitrogen 5, oxygen 6, fluorine 7. Borane then must have 3. Okay, so carbon, we know, to form its octet and be happy, forms 1 bond each with each valence electron. That's easy. Oxygen, right, just needs 2 electrons, so it just forms 2 bonds. Borane, even at max bondage, oh, that sounded weird. But anyways, even at the max bonding potential, can only form 3 bonds, and that at most gets it to 6. So this is octet, this is octet, but this is a sextet. And do you guys remember any other sextet species in this course? I'll remind you, carbocation is a sextet, and sextets in general are very, very electrophilic. So borane, which is pretty much a carbocation, is perpetually or always going to be an electrophile. So if anything, right, it's not going to attack any pi bond. The pi bond is going to attack it. Another way to think about this is that borane effectively replaces the position of a proton. So then this is really interesting, because then what does that then mean about the borane hydrogen bond? Because most AH bonds have a polarization where H is positive and A is negative, right? The acid is negative, the hydrogen is positive. Well, it turns out then, if borane is electrophilic, the hydrogen is actually nucleophilic. Interesting, we have a nucleophilic source of hydrogen. And so with all these observations in hand, we can actually explain why borane, right, sterically wants to go less sub, and electronically wants to go less sub. It is large, so it goes less sub, and it is an electrophile, so it goes less substituted. Or on that carbon, that does not stabilize a cation as well. So some pretty cool things there. One other cool little fact that I'll tell you guys about borane that most people, kind of gloss over. I think this is a cool fact. Borane is so electrophilic, you can't actually buy borane on the market. You have to buy B2H6, because boranes will actually do this weird sort of hydrogen bonding with itself. These dimers will form because they're electrophilic. They're trying to get electrons, and the way they do it is by sharing electrons via these like dimers. So that's how you get it. I think you have to like heat it up or something to break it. Another way to prevent B2H6 is to buy borane with THF, because THF, what it does is it stabilizes borane with a Lewis acid base adduct. And these are really easy to break. So it's just enough there that it stabilizes the borane, but it's pretty easy to break, especially if we have an alkene. Cool. So how does this reaction work? Well, like we said, borane likes to, add less sub, hydrogen likes to add more sub in this reaction because borane's larger. And so this is not a very traditional reaction. The first arrows are actually going to be a complex between the pi bond and borane, where the pi bond attacks borane and the hydrogen attacks the alkene. Okay, so hydrogen here, borane here, just like that. And so because there's 3 of these BH bonds, it's not that one of them is special. All of them can react. And this happens 2 more times. Okay, so I think you know what? I'll draw all 3. It's okay. No big deal. But borane is going to add to all 3 of these alkenes. So you don't actually really need a full equivalent of borane typically. You just need like 75% to 1 whole, 100%. So 1 to 0.75 is what I'm trying to say. You can use that and that tends to work. That's pretty fine. Okay. But really this here I think is the most important step. And it's the one that you guys should understand chemically in like as best as you can, right? Chemically, why is this happening? Borane is huge and it's electrophilic. As long as you understand that, I think you're fine. Because the second part of the mechanism is kind of weird, doesn't really make sense, and people kind of struggle with it. It's okay. I mean, everyone does. Even I have to like refresh myself on this because it's not entirely intuitive. But the second part of this mechanism actually begins with the reagent HOH, or peroxide. Kind of talked about peroxide. Peroxide is a little interesting because of this OO sigma bond. We've never really seen 2 heteroatoms bonded like that before. And this sigma bond actually, what it does is it makes, so NaOH, right, looks like peroxide, or peroxide looks like NaOH in that there's 2 OHs, but actually peroxide is slightly more acidic than NaOH because there's actually a dipole across the sigma bond that allows there to be stabilization. It's like an inductive effect. I think the term for it is sigma effect or something like that for peroxides. Anyways, this allows us to be a little more acidic than OH minus. So we form a bunch of these peroxide anions. And these peroxide anions, again, if borane is electrophilic, peroxide anions is going to attack it. That's like a no-brainer. That makes sense, right? That would happen. Totally what's going to happen. And what forms are the sort of, do they call boronate esters? I'm not really sure what they're called, but it forms this complex here. Okay. Now, again, keep in mind that borane, that should be a minus charge, sorry. Borane is not electronegative, so it doesn't really like this minus charge, and it really wants to get rid of it. Okay. So one thing it could do is just kick off the O minus. It could do that, but that wouldn't really solve our problem. What it's really going to do is this really weird mechanism. So don't worry if this doesn't make sense. Just kind of memorize the arrows. One time I'll say memorization is okay. But this bond here, any of the 3 alkyl bonds to borane, one of them will do it. It will attack the first oxygen, and that will kick off the other oxygen. Really, really weird. But that's what ends up happening. Okay. And so when it does that, what we get is this here. And this is actually great because remember, one part of this reaction was just tricking the molecule to add the electrophile, but the other part was we had to somehow turn that electrophile into oxygen. And this is how we do it. We trick the molecule into attacking an oxygen. We trick the molecule into making the alkyl group attack an oxygen to place that oxygen in that position there. Now all we really have to do is replace all of this with hydrogen, and we're going to make our alcohol. So how do we do that? Well, we're not quite done here yet. That OH minus that just fell off is going to reattack the borane because it's electrophilic. Will form, again, that really, anionically charged borane that doesn't like to exist. And how does it resolve itself now? Well, in this case, right, all we had to do is kick off the oxygenated alkyl group. And what we get is the following. Now, this is going to get protonated in solution, probably by like water or something. So we can throw a proton on here. Even this OH actually can participate in protonate. Doesn't really matter. But now we form that alcohol that goes on that less subbed carbon. And so again, if we think about what's going to result from this, we're going to form, or if you think about the fact that there's 2 more of these alkyl groups here, all the alkyl groups in this reaction will react So this will happen 2 more times, and what will form is 3 of these alcohols. Okay, cool. So again, how does this reaction work? We trick the molecule into adding an electrophilic component that we can transform into an alcohol. Okay, and lucky for us, we can do 3 of these. You can do 3 of these reactions on one borane. So I guess it's a little effective. The only thing is that borane is actually really toxic. I think it's carcinogenic. So it's actually not the best thing in the world. It's kind of terrible, but no worries. We can use it if we have to. Cool. I think the other thing in this reaction, if I remember correctly, I think it's boronic acid, right? I think it's boronic acid. I think it's H3BO3 that forms. And if it's in basic solution, it's probably actually completely deprotonated. It's probably Na3BO3, something like that. That's just something, it's just a byproduct. You don't have to know it, but just including it just in case. Okay. So I know we took up the whole page with mechanism here, but don't be fooled. We don't need to know the whole or we do need to know the mechanism, but the part that matters is this first part. So we can take actually the next page now to sort of talk about, different reactions. But even with one propene, we see a difference when using BH3. We end up seeing that we would get this alcohol here, right? Which is so different from the other alcohol. I guess if we wanted to show intermediates, we can show this one, but we get this alcohol here, right? Even the isobutene example, immediately we see a difference in that we get this alcohol here. Normally we get the alcohol here, we get it here, right? Now we're getting a switch in that regioselectivity, right? That's the power of this reaction. Here's one thing, you actually would not do this reaction with a non-regiochemical alkene. It makes absolutely no sense to do this because the point of this reaction is to differentiate, right, that less stable carbon from the more stable one, or the less sub from the more sub. So it wouldn't really make sense to do this reaction here because we already have 2 reactions that add how we would want to on a non-regioselective. So we're never really going to see this reaction done on these guys. It would be literally a waste of time and money. And your PI would be really mad at you. But once again, if we think about I use this one in this example, a rearrangeable one, but even the rearranging one is not going to rearrange because at no point in time do we form anything cationic in this reaction. Okay, so what we get is this here. I actually know for a fact that this is a common target. So this is how we make this common target. You can't really do this reaction with alcohols. At least I haven't seen it done with alcohols. So I wouldn't say that this is generalizable. This is purely just a hydration. So you can only do this with OH. I wouldn't try to do this with ROH. Okay. Oh, I realized I didn't really show like the full reagent condition, but BH3THF and the second step would be HOH-NaOH. Okay, so that would be like the reagent condition. This would be 1, this would be 2. Okay, cool. So one really cool question that kind of comes out of these reactions with boranes is the following. So this is sort of like a concept question to see if you're paying attention. Okay. Let's say I wanted to react this with borane. Okay. And specifically, I want to react this with R2BH. What is R2BH? R2BH is BH3, but it only has the ability to react once. So even though, we could react with 3, whenever we have more than 1 pi bond on a molecule, we only want to use R2BH because we could accidentally complexate multiple times and actually turn off the reaction. So whenever you have multiple pi bonds or you're trying to react with 1 pi bond, right? So I kind of given away that we want to react with one of these guys, R2BH is going to be employed. Okay, so what do we think is going to be the answer to this problem if we use R2BH and use what we've learned before, right? Maybe even try drawing out the intermediate and see which one will be better. Cool. So hopefully you guys tried that and hopefully it wasn't too hard. But remember, the idea is that borane is electrophilic and it is huge. So in terms of electrophilicity, right, both of these are alkenes. They both have electrons. But really the thing is going to be the steric argument, and that borane is huge. So if borane is going to go anywhere, right, it can go here, it can go here, it can go here, it can go here, right? Which spot has more clearance for that huge boring? That circle is supposed to be boring, right? The spot is going to be the terminal end. And so hydroboration oxidations have a big preference for terminal or as less sub as possible positions. Okay, you're not really going to see reactions done on highly substituted alkenes if there is a less sub alkene available. And this will again turn into this alcohol here. So this actually, there's a term for this when we have a preference for one alkene over the other. This is known as chemoselectivity. And at the very end of this video, we will briefly consider the chemoselectivity of all reactions possible, but that will be towards the end, which hopefully is in half an hour. I'm going to try to, so I'm going to have to speed up a little bit. I apologize. Cool. So that is the hydroboration oxidation. And once again, all it is a matter of, let's say I have this alkene here. Oh, actually, let's do this. You have this alkene here, right? We're going to add hydrogen to the more sub side and oxygen to the less sub side. Okay, but whoa, wait a minute. This reaction forms two chiral centers. So before we move on, we do need to talk about the chiral centers. For the sake of time, I'm just going to make this really quick. Because of the complexation step here, boron and hydrogen actually have to add on the same side. So this reaction is very selective for syn. Stereochemistry, you will practically never get anti. So it's very much syn. So what we're going to get is the wedge OH as such. And we're going to get the wedge H here. Okay. Keep in mind that this is, there is no reason why only the wedge would form here. We'd also get the dash one. So we would also get this here. Cool. Apologize. I know I normally take more time to talk about this, but we're really pushing it. I think it's 32.5. We want to get this done, done in at least 3 or less. Cool. All right. So the other reaction that we wanted to consider was, okay, now we can turn this into alcohols like this, but what if I wanted to put like a halogen here? Could we do that? The answer is yes, but there's a bit of a caveat. We can only do this with one kind of alcohol. Okay, use green. We can only do this with bromides. So how do I do this reaction here? We call this radical halogenation, which that might be a little bit confusing, considering that we have a different kind of radical halogenation as well. So no worries, this is alkene radical halogenation. So how does this work? Well, as the name suggests, we're going to be using radicals, which are not the favorite, but the reagents are going to look something like this: Br2, or sorry, HBr, and ROR. Okay, so how does this work? Well, with any radical reaction, we have an initiation. Okay, we have an initiation. In this case, the initiation is actually going to be of the radical. Sorry, the peroxide. So peroxides are really, really reactive. They're kind of actually a problem. In HV or even in sunlight, like these guys will just pull apart their bond. I mentioned that this bond is particularly special and interesting, and this is one of the reasons. They will readily form these peroxide radicals. So radicals are kind of a boohoo kind of situation. We kind of don't like them, but they can form. And when they do, right, initiation, we form two radicals. They're going to want to react. One of the things with radicals is that radicals are kind of a proton scavenger. And specifically, peroxide radicals are super proton scavengers. Like these guys are, if you're forming them, the reason is pretty much almost 99% of the time it's because it's pulling off a proton somewhere. So if we think about the best proton to pull off on any of these things, it's probably going to be from HBr. So I know I'm calling this a propagation. Some people like to call this also an initiation. It's really up to you. I call it propagation because it follows the rule of propagation, which is, the formation of radicals is, or the gain or loss of radicals is non-existent. It's the same. right? So we have one radical on this side, and we're going to have another radical on this side. So that's why I call it a propagation, but some people might call this, they call this pre-initiation and they call this initiation. You know, up to you what you want to call it. I'm just going to put it in propagation because that's what it follows the rules of. So now we have a bromine radical. And again, right, when we do our reaction with this bromine radical, it's going to be with the alkyl or the alkenyl, alkene. And the bromide, right, will form a bond with those pi electrons. Now there's sort of two things we could do here. One that I've shown in there, right, with these arrows, which would form this radical. And there's another set of electron, there's another set of movement we can do, like this, and this would form this radical. So take like no more than a couple seconds. I will also only take a couple seconds, but think about which one's better. It helps if you know that radicals are electron deficient. And so if they're electron deficient, they should follow the same rules as our, stability down here. Radicals are pretty much like only worry about them for hyperconjugation. They're also resonance stabilized, but that's something for midterm 2 that we'll worry about. But anyways, using this sort of hierarchy here, very, very easy to follow. It's going to be the secondary radical that's better. And that's the radical that we form. And so here is where we finally tricked the molecule, because we tricked the molecule into adding bromine, but forming, added bromine as an electrophile, but forming, a very stable radical on that more subcarbon. So when this radical, this alkyl radical here, reacts, again, it'll be with HBr. We have successfully added a hydrogen to that nucleophile position and bromine to that electrophile position. So very, very cool thing that this reaction accomplishes. There is a termination. And again, if I had more time, I'd go through it, but I don't. I'm trying to finish this very quickly. I apologize. But there is a termination. If you wanted to terminate, you could. You just terminate all the different types of radicals. I'll draw all the radicals that you have in the system, and you can think about how they would terminate. I'm just not going to do them at all because I don't have the time. But all three of these can combine and terminate each other and form some pretty wacky products. But the cool thing about this reaction is if you think about it from the HBr perspective, like that we learned before, what we do is we add an electrophile to form a reactive intermediate, and then we add a nucleophile, right? So add an electrophile, reactive intermediate, add a nucleophile. And that's how we got, the placement of Br in the more sub, placement of H on the less sub. What this reaction does so cleverly is it follows the same sequence. We add an electrophile for sure, right, to form a stable intermediate, but the electrophile we just switched, right? We turned it into a bromine. So that's what makes this reaction a little bit cool. It tricks the molecule once again into doing something for us, but doing it, legally within the rules. Cool. So that's where I'm going to call it for this. The racemizations or, stereochemical outcomes of this reaction are the same as HX. So stereoselectivity, same as HX. So it's non-stereoselective. Right. But keep in mind that, there is that, I guess you could say that there is that one set that is stereoselective if it's tetrasub. Hopefully you'll never have to see that though. Cool. So same stereoselectivity. I apologize. I know I've really kicked up the speed here. I'm just trying to get through these as fast as possible. Cool. So with that being said, we've finally gotten through our third class of reactions. Our first class being, right, the cationics, second class being the cyclics, our third class now being the sort of Trojan horses, like the guys that kind of do things on their own. The last, I hope there's only 3 more. I think there's 3 more reactions. The last 3 reactions are going to just be what I consider oddballs. They kind of just do things because they do. And I personally couldn't think of a way to, I couldn't personally think of a way to add them in a group that made sense. So I kind of just all lump them together. They all just do things that don't follow the other mechanisms as well. But I will say this, they do all have sort of cyclic intermediates in a sense. So we can consider those reactions now. The first one is actually going to be H2PD, which is it might be interesting to a couple of you because H2PD tends to be the first reaction covered in a lot of textbooks. I just like to cover it last because, again, it doesn't really fit the mold of many of the reactions that you guys learn. Cool. So now we're just going to cover what I consider oddballs, H2PD being the first one. So H2PD, what is it? I think it's better to just look at what happens to this reaction when we do it, but we basically take a metal catalyst, just push some H2 gas on it, and that H2 gas adds across the pi bond. So literally what it does is this, it just makes the pi bond disappear. If I do this reaction with isobutene, same exact thing. Okay. It just makes the pi bond disappear. So clearly what we're doing is a hydrogenation, right? We're just literally adding H across the pi bond. And it's like the simplest reaction, which is why people like to start with it. But its mechanism is not very simple. One last reaction that I'll kind of cover on this is the, there really, it might appear that there's some regiochemistry, there really isn't. Once again, if we're adding two of the same thing, right? Who cares how it adds regiochemically? No one cares. So it doesn't really matter as of right now, regiochemically how things are working. But we should look at mechanism to still kind of understand what's going on, because let's say, for example, that I hydrogenate this pi bond here. Okay, let's say I add an H2PD. We will be forming chiral centers in this reaction, right? And specifically, the chiral centers we form syn. So a little bit interesting. I'm taking a little bit of a different approach here. I'm showing you the stereochemistry now so that we can make sense of it in the mechanism. So we get syn addition. Once again, this will be a racemic. Okay, so that's something we'll have to worry about. But again, syn addition. So how can our mechanism account for this? Well, you might remember that our last syn addition did a pi bond complexation where both components complexated on the same side and had to therefore add on the same side. And that's actually the same thing that's happening here. So I guess actually we did know the mechanism. I didn't have to do all this dramatic stuff. Anyways, so how does this work? So if I have H2 and I shoot it on the metal, what's basically happening is the metal surface is holding that H2. So this is what it looks like. It's holding that H2. The pi bond then, right, whenever it comes, will come and literally just fly into the catalyst. Okay, so actually I like showing it. It will literally just be floating around and eventually just come down and slap onto the catalyst. When it does that, sort of complexates with these two hydrogens here, and it will just add them on. Okay, so add it on just like that. Very, very simple, this mechanism. And I'm not actually sure how they even proved it. I think they literally just, I think this is one of those mechanisms where we're just really sure it has to be this because of the stereochemistry. And just, I really wonder how they figured this out. I don't really know. But yeah, so what you really just need is some metal catalyst. There's a couple of them. There's palladium, there's platinum. So PT, sometimes you'll see PT. PT works too. Anything with H2 just adds it on and you move on with your day. Okay. So when we take examples that are a little like this, right, where we can form, so let me actually let's keep a simple one. So we'll keep this one here. Actually, yeah, let's keep this one here. So when we think of like a chiral, right, or a alkene that can become chiral, there's actually a term for that. It's called prochiral, by the way, if you guys didn't know. So let's say we had this here and we had like a center that, like, let's just use the same one as before, right? We have this one here, right? When this complexates, right, this has to add on the same side of the pi bond. Like boom, like that, like take on the same side. No way around it. And what we get are syn centers. So again, this has to have added on the same side. So I guess we can say then that if this is wedge, then dash here would have to be, let's say, methyl, So dash here has to be ethyl, and then in the plane, we'll put ethyl and methyl. Okay, something like that. Cool. So because we're adding two of the same thing, just like we saw with OH and we saw with X2, there is one question we could ask ourselves, and that's, what if I were able to make a meso compound, and you have to use a syn symmetrical. So syn symmetrical alkene, disubsyn. If you do H2 addition across this, we're going to use D2 here. Sometimes you'll see PT, so I'll add PT this time. What you're going to get is a syn addition as such. Oops, sorry, this would be deuterium. We'll get a syn addition just like that. And again, we can ask ourselves the question, right? Like, notice how the deuteriums are all syn. The hydrogens are syn. And the methyls are syn. So this has to be meso. Again, the idea of meso is just that all the like groups carry the same relationship. So whether it's all syn or all anti, right? That's how you can get a meso compound. So that's something we have to consider here. So as long as you're hydrogenating synphase and it forms a chiral center and you're accounting for that, you should be pretty much good. The only significant example is when you consider the following molecule. Apologize with this time crunch and starting to do less organized examples. I apologize. So let's say we have this here, but what I'm going to add to this is going to be this here. So neat little stereochemistry. So actually go ahead and try this on your own. Let's say we added D2 PT. What do you guys think the answer is? Okay, clearly I'm making a big deal of this for some reason. So what do we think the answer is? Pause and try that. So the best way to think about this problem is to draw palladium catalyst both on the top and on the bottom. Because remember, metals, like it's not exactly one, 2D surface. They're 3D surfaces. So there's metal all over the place, but thinking up and down for now is good. I used to make a joke here. If I had more time, I'd make it, but clearly I don't. I used to make this joke that this is like I guess this reminds me of that one Pokemon. Loudred, I think. Looks ridiculous, but I'll just keep it on here. Anyways, what you can think of is sort of like a Loudred eating a cyclohexene chip. So let's say a Loudred eats a cyclohexene chip, okay? And in order for Loudred to eat this chip, it needs to close its mouth all the way to crunch down on it, right? I mean, everyone does this, right? In order to crunch down on something, you need to bite down, right? Well, when Loudred bites down, let's say from the top, so let's say the top of Loudred's mouth comes down first. Okay, Loudred is it going to hit the chip? Is Loudred going to be able to crunch down on its chip? Let's put this here. Maybe it'll make more sense, right? When Loudred tries to crunch down, is it going to be able to crunch down on its chip, right? Is it going to be able to hit that alkene? The answer is no, because look, that Loudred's teeth are clashing into that steric cyclopropene. So it's trying to get there, but it can't. It's like, oh, dude, what? Like, what is this? It's like the roof of its mouth is getting eviscerated by this 3D chip, 3D cyclopropane. Okay. On the other hand, if it tried to, munch on this chip with its, bottom set of teeth, as if it's, using each jaw separately. I don't know why I would do that, or each set of teeth separately. But if it tried to from the bottom, notice how the bottom breaches that alkene. So it can reach the alkene, no problem at all. Now, that was probably a really confusing analogy, and I'm not really sure why I doubled down on using it. But the point that I'm really just trying to make here is that if we have local stereochemistry, as we've seen, And really it can be anywhere on the molecule because H2 is a 3D catalyst, right? It's like an enzyme pocket, you think. The hydrogenation or deterioration is always going to happen opposite to that stereochemistry. Always, always. This is the only isomer that forms in high yield. Okay, it's still syn, but it will never, right, go through the pain of trying to form this here, where these H's are on the same side. You almost never see this. It's like 99 to 1. I think sometimes it accidentally does it. Okay. So that's the point that's to be made there. Again, local stereochemistry affecting our reaction again, right? The last time we saw this was all the way back here a couple hours ago, right? Where a CH3 was acting as a helicopter, preventing things from adding on. Now what it is we have a cyclopropane that is acting as a I don't even know. It's acting as a deterrent from hydrogenation on the same phase. Cool. So that is the significance of H2PD. Again, not a very crazy reaction. So that's why I'm okay with shoving it towards the end. Again, it's just really, I mean, visually, you're making alkenes you're turning alkenes into alkanes. You're just poofing the alkane there. Just keep in mind that it's a syn reaction, right? It's a syn stereoselectivity there. And actually, in some cases, it's syn stereospecific because it's only forming this one thing here. Okay, that's how stereoselective is. We can almost call it stereospecific. Cool. All right. Now, this cyclopropene that's causing problems, we can actually make it with a really interesting reagent. There's actually whole classes devoted to this kind of reagent. So it's interesting that you guys cover this for like a couple seconds, but we can use things known as carbenes to make that cyclopropane that was such an issue earlier. Okay, so what is a carbene? Carbenes require a little bit of prep actually to make them. One of the reagents we can use on them is something known as diazomethane. Diazomethane is CH2N2. Okay, so what is CH2N2? Looking at it, may not look very significant, but if we draw out the Lewis structure, this is what CH2N2 looks like. Okay, so we have a carb anion and we have a nitrogen cation. Now, one thing I want you guys to look at here, if you ever see this again in this course, which you will, just when I'm mentioning it, but if you ever see this again, I want you guys to always remember that this thing will always do what I'm about to do. If you ever see N2, N2 is the #1 leaving group in the world. I know you think I'm just exaggerating. I'm literally being serious. N2 is the best leaving group in the world. There is nothing in the world that leaves better than N2. If you ever need something to leave, you just turn it into N2. And there's many ways to do that you'll learn in 118C. Anytime you have an N2, N2 will literally fall apart. Even to like, I think the only way to really prepare this is at very low temperatures. But you heat this up a little bit, and N2 literally flies off. Okay, so N2 is literally going to fly off. No questions asked. Okay, so this is an interesting thing because carbon is anionically charged. So it's anionically charged, but carbon is also losing a leaving group. And normally when carbon loses a leaving group, what charge do we give it? We give it a cation. So this structure here that we're going to draw is actually a carb anion and a carbocation both in one. This is known as a carbene. And carbenes are also depicted as just, carbons with two other groups in a lone pair. But I think that lone pair can sometimes be a little bit confusing for some people because you think it's anionic. But really the better depiction is that it's both an anion and a carb and a cation on the same thing. Very common depiction of the carbene molecule. If you look at a carbene, it's very easy to see why it's so reactive because it is a carbon with two groups and a lone pair. You guys need a reminder of what this looks like. Here it is, right? It is basically like a borane. So yeah, it does have some nucleophilic power, but it is very, very electrophilic despite having that lone pair. And it is that lone pair, or is that electrophilic character that assists in this reaction to form a cyclopropane. So if you want to, you can go ahead and try this on your own. I guess I could have included this in the cyclics. I guess I could have. So maybe that's a note for in the future to include this in the cyclics. But I think it's just such a weirdo. It kind of, it's in its own category. But you can imagine, right? We attack the carbene and we attack with the carbene. I think if you use the plus minus nomenclature or like signage, it makes a lot of sense how to use it. Because in a way, right, we're attacking the cation and the anion is attacking back. And that's how we make our cyclopropane. So one way to do this is with CH2N2. Again, very, very iconic way of making this. Some lesser known ways, or not lesser known, but I don't want to say lesser known, but other ways of making it that are not very obvious. One way being with chloroform and terbutoxide. Okay, cool. So again, we are trying to somehow replicate this scenario where we have a carb anion that has a leaving group, right? That has like a leaving group on it. If we look at chloroform, it is, 3 Cls and an H, right? Making the carb anion part is really easy once you remember that terbutoxide is a base. So that base is going to pull off that proton, right? And form that anion very easily. The next part is the part that I guess now should make a little more sense, right? If all we need to do now is have a leaving group leave, then you have 3 chlorines. So any of these chlorines will do it. It's good enough. And once again, we've got that anion cation feature. Now, the cool thing about this one is that this is not a CH2 carbene, it's a CCl2 carbene. So when we have this one, we actually form a carbene with 2 chlorines on it. This is really cool because in some, this is not something you might expect in our class, but in some parts of like organic synthesis, you can actually use these chlorines as leaving groups, because if one of these chlorines were to leave for some reason, you can form this cation here. And I know that this cation looks bad, but actually chlorine stabilizes this cation with resonance. So this is a stabilized cation, and this cation allows you to do some pretty crazy things. One crazy thing actually that allows you to do is ring expansions. So let's say I had like say I had this system here. This methoxy can actually assist in a ring expansion because this group here will fall, this cyclopropane, remember, propanes don't like being propane, so they'll open up for any reason. A good reason is to open up to become a cycloheptane. This is going to be really hard to track. Don't worry if it's hard to track, but basically this is what's going to form from that opening. I can quickly label these carbons 1, 2, 3, 4, 5, 6, and 7. So 1, 2, 3, 4, 5, 6, and 7, right? Between 6 and 7, we're forming the new pi bond. There is now going to be a cation on 1, and that cation can be resolved with a pi bond. So pretty cool thing. This is just a cool offside reaction. You could also even skip this if you really wanted to. I just wanted to show you this really cool reaction that I've seen done before. But really, the possibilities are endless with carbenes. They're kind of the weirdos in this. Now, the nice thing here is that because we're forming a cycle, all you really have to worry about is that you can form a wedge cycle and a dash cycle. It doesn't really matter. Most people, when they test on these kind of concepts, all they really test is the fact that you're making a cyclopropane. That's pretty much good enough for most people. Just know that for this guy here, diazomethane, gives you, right, a CH2 here. Chloroform and terbutoxide gives you a CCl2. The last really cool thing you can do with carbenes, or the last one that works, is like, I think it's zinc, copper, and something. Sorry, I'm gonna have to actually, what was it again? Okay, I'm just gonna look this up because I can't remember. So I just need to look this up now. Oh, that was simple. CH2I2. This just makes that carbene as such. Very simple. The cool thing about this is this actually doesn't make a carbene. It makes what we call a carbene equivalent. Essentially, it makes CH2s that are bound to zinc and iodide. And so these guys here, so a way to think about this is that carbon is stealing electrons from zinc. So it's anionic here, but iodide is stealing electrons from carbon. So it's cationic here. So it follows that same sort of minus plus thing with carbenes that we tend to see. So it forms something like this. You wouldn't need to know mechanism because it's very complex, but do recognize that this is a carbene. You could just recognize a CH2 there. It just makes a carbene like that. All right, that's all we got to know about carbenes. Nothing much else there. And for the sake of time, we do have to unfortunately move on. All right. This reaction here does actually have a relative to the previous reactions. The only reason why I included it in here is just because its mechanism, again, doesn't help us too much in, it really doesn't have like a similar mechanism. It kind of does actually with the last reaction we'll talk about after this. So we're almost there. We're almost there to the last one. I apologize. I know this is long. We're almost there to the last one. But there is, this reaction we have to consider. And that is the OSO4 reaction. Okay. So OSO4, what does it do? It gives us a cyclic intermediate. I was going to tell you what it made, but I think it's better just do mechanism first. So it's always easy to do this on the syn alkenes because you can put everything in the same way. But OSO4, what it looks like is this. And much like everything else that we've been seeing in this section, aside from the carbenes, right? When we have, something approaching a pi bond, right, especially from the same side, right, these things can interact. And the way that they interact is that the oxygens, right, sort of attack and become attacked. Okay, so we sort of see something like this. I believe it to be that arrow. I think I might have messed up one of these arrows. Let me think. No. Yeah, it has to be something like this. So we'll just, whatever, we'll keep it like this. Maybe we'll do this here. Okay. Anyways, the idea is just that we're attacking these two oxygens on one side of the osmium. There we go. So we're attacking one of the sides of this osmium. Doing so, right, gives us an oxygen here and an oxygen here, right, bound to osmium. And this here. And so this is very, very simple, right? Because you can kind of see where this is going. But if the pi bond is added to oxygens, it's not because we want this whole osmium complex. It's because we want whatever this osmium gives us, which is those two oxygens. So we can do a reductive workup here, which you don't need to know the mechanism for, thankfully. But what that gives us then is 2 alcohols. Okay. As you can imagine, like just like with H2PD, just like with BH3, our other syns, because we're delivering to the same phase, this has to be a syn addition. And just like with H2PD, whenever we deliver 2 of the same things, and same thing with X2, we have to consider, is there a way to make this a meso compound? And we can, again, as long as we react this with a syn symmetric alkene. Okay, as long as we do that, totally going to make a meso compound. Now, also, it's the same as H2 and X2. Because we're adding 2 oxygens, who cares about regiochemistry? No one does. No one does at all. No regiochemistry whatsoever, because we're just adding 2 O's. So nothing to worry about. So these are always everyone's favorite reactions because you just literally see OSO4. And you can think OH, OH on the same side. And this is racemic, right? Again, unless it's syn symmetrical, so disub syn symmetrical, you're gonna make racemic compounds, or if it's achiral, right? Meso is only possible from here. But even our regiochemical alkenes doesn't really matter. Let's say now I make the dash OH, right? This is going to be racemic as well. Cool. This reaction, very simple. Not much there is to it. although there is like a, osmium is not terribly good for you. So there is a way to do this reaction that's a little more safer. It's catalytic osmium with peroxide. You might see that sometimes. Don't be afraid. It's now just that the peroxide, what it does is every time osmium reacts, the peroxide just re-gives it the two oxygens it just lost, because the reductive sulfur is just doing that. This reductive stuff is basically just cutting those bonds. So it's like osmium O2. H2O2 just re-provides those two oxygens back. That's all it's doing. There is an older method actually of doing this dihydroxylation. That's the term for this, by the way, dihydroxylation. Okay. And it's with KMnO4. But the issue with KMnO4 is that you have to do KMnO4 cold, like really, really cold, in order for it to work. Because if it's not cold, if it's actually hot, it will actually do a cleavage down the middle there, where it turns these into carboxylic acids. And sometimes we don't want that. Sometimes we really don't want to cleave our bonds like that. So that's physically, or like visually, what is that we're doing is we're cutting down the bond like that. And we don't always really want that. So that's why KMnO4, we don't really use it anymore. But in the lab, you will use it because it's still a very good test, a very common test used today to test for the presence of an alkene. So KMnO4 actually uses stain all the time. If you want to make sure your alkene reacted, like let's say I have a molecule like this, right? One of my molecules actually looks like this, and I did a reaction. To make sure that it reacted, I can use KMnO4 and see if it stains. Because if it stains, I just messed up, because that means that double bond is there. What I want there is for there to be no double bond, or my reaction to have gone through. If KMnO4 stains this or reacts with this, something is wrong. Cool thing is I think it's purple and it goes like brown or something. So it would be sorry. So KMnO4 is purple, but if it reacts, right? If KMnO4 reacts with the let me put it here actually. If KMnO4 reacts with this, it'll turn brown, the solution. So that's like your KMnO4 test. It's what we call a test of unsaturation to see if there's a pi bond there. Cool. So actually, this reaction here, if you want to do it, there is a better way to do it, a more intentional way, and that is going to be the very final reaction. Thank the Lord, and that's going to be O3. Ozonolysis is what we call it. Okay. So how does ozonolysis work? Ozonolysis is going to be a class of reactions that you will not touch until midterm 2, but we just include it because it's type of reaction. It's known as a cycloaddition. And cycloadditions, pretty much the only way to explain them is orbitals. There's really no other way you can explain a cycloaddition. It doesn't make sense unless you know about orbitals. So we're not going to try to understand this reaction other than to say that we will learn a lot more about orbitals later on, and then we can use orbitals later on to explain why this happens. Okay, but not like it really matters. It doesn't really matter at the end of the day. The only thing that I tell you guys to recognize is that O3 is what we call a 1,3 dipolar reagent. Okay, so why we call it a 1,3 dipolar reagent? It's because there are 3 atoms conjoined where 2 of them next to each other are polarized, minus and positive. Okay, so 3 atoms bound together, we form this dipolar reagent. And so it shouldn't surprise you then that the cycloaddition that we're doing is known as a 1,3 dipolar cycloaddition. So how does it work? Very, very simple. We're going to do our standard arrows of attacking and being attacked. And what we're initially going to form here is known as a malazonide, I think. The way I remember the malazonide is that it's these 3 oxygens together, and these 3 oxygens hate each other. They're really mad. They don't want to be here at all. So when we do this 1,3 dipolar cycloaddition, actually, it's very funny. The molecule realizes that it didn't want to do it in the first place. So it does it, and it's like, oh, no, wait, I did not want to do that. I definitely am not happy in this state. So what does it do to sort of, alleviate this? It undoes the cycloaddition, but it does it really specifically. The way that I recommend you guys do this to make sure you don't mess this up is choose one of these 2 bonds here between the oxygens, and whichever direction you break in, just commit to that direction and you'll be fine. So break that between carbon and oxygen here, then break this bond here, and then break this bond on this oxygen. Okay. So again, just to go over that again, choose one of these two bonds. I'll choose this one this time. Just do that there, put that there, move this here. Okay. And then move these electrons onto this oxygen. Okay. If you do this correctly, this is what you're going to get. On the left side, we are forming a double bond between oxygen, and you're breaking this portion off from the rest of this. So basically what you're doing is you're breaking off this portion from the rest of this. So what you should get is a carbonyl like this. Okay. On the other side, this is where things get a little crazy. Oh wait, did I just undo everything? I did something wrong here. Oh, sorry. I did an extra set of arrows. So even I mess this up sometimes, so I apologize. So let's retry this. I apologize. So you definitely still do want to choose one of these two arrows. But what you're going to do, again, is move that there and move that there. And that's all you want to do. Okay. That's the way we're going to decompose. If you do 3 arrows, you're accidentally going to form something that cannot be formed. It's only going to be 2 arrows. So luckily, we don't actually have to break this here. I apologize. So you can do it this way, or you can do it the other way too. Just so let me draw this up. So we can do it this way, break this bond here and then this bond here, or we can break this bond here and this bond here. Whichever one you want, just choose it. But if you do this correctly, what you're going to do is you're basically forming 2 compounds. Okay, one compound you're forming this. Okay, so how do I know that I'm forming this? What you want to look for here is this arrow here. So if you're wherever you're breaking this OO bond, man, this is really hard to explain. I think about this. I guess you just kind of have to follow the logic. So here's what I'll do. I'll draw this 2 different ways. I apologize. I've been sitting here for like 3 hours now. My brain is mushing a little bit. So what I'll do, instead of butchering an explanation, is I'll just draw the 2 different arrows, and you can look for a pattern. And in the future, I'll update this, or I'll put in the description update or something that gives like a better answer for all this. But if you decompose this way, which you can look at, you're forming these 2 things here. Okay. If you decompose this way, what you're forming is this here. So it doesn't really matter which way you do it. I know they look different, but trust me, at the end of the day, it won't matter. All that matters here is you just look at both of these and you just choose one. So again, I apologize. I know that I'm doing a terrible job with this. But the point is that we're going to decompose this way or this way. Regardless of which way you do it, the common theme is that you get one compound that has an OO, where there's a positive and a minus, and then you get just a normal carbonyl compound. This compound here, it's like a carbonyl with an oxygen, is known as a carbonyl oxide. And the carbonyl oxide should look familiar. It should look like something else on this page. If it's not totally obvious, carbonyl oxide looks like O3 in that it's 3 atoms. I know this is 4 atoms, but just focus on these 3 atoms here. We have 3 atoms conjoined where 2 of them have a dipole. And the reason why this is important is because if we have this 3 atom configuration, we can do a cycloaddition. So would it surprise you guys if we did another 1,3 dipolar? Hopefully it doesn't. This 1,3 cyclodipolar, although, is actually very specific. It's always going to happen like this, where the oxygen always attacks the carbonyl carbon. Okay, so it's always going to be that, which makes sense. Carbonyl carbons are electrophilic, so it makes sense that the anion wants to attack there. But this is what we're going to get. I'm just going to focus on this one here, again, just for sake of time. But what we form is this really crazy monstrosity here. Now, if you've been paying attention, right, clearly these compounds are not very stable. And so a good question is this going to decompose? And the answer is yeah. But what you use to decompose it will, determine a lot for this reaction. So there's typically 3 routes you can go. Peroxide, when decomposing this, it will decompose the system, but it will give you the most oxidized form of this decomposition. So actually, let's do this first. So peroxide is known as like the oxidizing scenario. Okay. Zinc, I believe, or sulfur. So you can use zinc or sulfur here. So you typically see this, or you see CH3 2S. Either one of these two will work. This is sort of the, I guess, I think of it as a neutral, like kind of a neutral condition. You'll see what I mean by that. The last one, I think it's NaBH4 actually. Yeah, I think it's NaBH4. NaBH4 is known as the reducing condition. Okay, so why am I telling you all this? Is because what you use will determine what is the total oxidation state of your molecule. And if I do the neutral condition breakdown, I think the rest of this will make a little more sense. But this is kind of how it works. If let's say I have, for example, sulfur here. Sulfur really likes oxygen. And so it will take this oxygen here. Okay. Or, I think it just kind of chooses one of these. That's kind of the idea that I get with this one. And then this molecule will just kind of decompose off of that. So how will it decompose? Like that and like that. Okay. So again, one of these 2 oxygens, you get to, I think, which one would I choose? I'm not sure which one I would choose. Maybe the one that's closer to this oxygen. I really hope your professors never make you know this mechanism, because even, I mean, if I can't figure this out on my own right now, how can you guys do it, right? But anyways, sulfur is going to take this oxygen here. I always choose one of these 2. I don't think it matters. Hopefully it doesn't. And then to kind of finish this off, just break this bond here and break this bond here. Okay. By doing so, what you form is this, and then a sulfur oxide like that. Okay. So what I'm trying to do here is trying to put these in the same area generally as everything else, so you can kind of see how things broke down here. Right, like how did, where did everything go? I think it helps. This is actually DMSO. This is this solvent that you guys are using all the time in 118A. But that's how this kind of breaks down. You form these 2 carbonyl compounds. We don't really care too much about DMSO. So the thing is that these compounds do sort of the same thing, right, in breakdown. It's just going to either oxidize or reduce your components. So if I were to, let's say, reduce a aldehyde, I get a primary alcohol. So in this reaction condition, I don't get aldehydes, I get alcohols. I imagine, I'm not sure the DMSO shows up, so I won't even bother with that. Okay. And the H2O2, component, where we're over oxidizing, we're just turning all of our aldehydes and formaldehydes into carboxylic acids. Cool. So I know that this is actually probably the worst mechanism out of them all. I think this one makes the boring one look like, an acid mechanism. Luckily for you guys, this is actually very simple. This reaction is not actually that hard visually, because visually all you're doing is what I showed on this page here. You're literally just chopping across the pi bond and forming the 2 carbonyls that would come from it. So the way that people like to do it is they do that chop. So I do it like this, and they put an oxygen at the end of each carbon. So that's what you can do there, if you'd like. Oh, sorry, not that. So that's basically what you're doing. So I can give you really any of these compounds, and really all you're doing is sort of separating the pi bond, and at that cut putting an oxygen. That's the ozonolysis, especially ozonolysis in that reductive environment. Okay, Again, if you're just doing it in oxidizing environment or reducing, you're just changing these to that respective redox level. But that's all you're really doing. And so the real utility here is that this is, we've learned in the past carbon-carbon bond forming reactions. This is your one and only carbon-carbon bond breaking reaction. So this is what makes this reaction so, so important, because in synthesis, if you ever see a reduction of carbon chain, you know that it will be an ozanolysis, 100%, no doubt about it. It'll be ozanolysis. Last cool example that I'll leave with you guys here is that because it has this bond breaking ability, there's actually a structure that used to be kind of untouchable and stable that we can now destroy. If I have a cyclohexene and I do O3 with zinc, let's say, this will break open the ring. So we'll form, you can do that. You can unravel this 2, 3, 4, 5, 6. What we get is these two guys here. Okay. So pretty cool that we can do ring breakings now. And that is the final reaction. So I apologize for this. I know this last section of reactions, I really rushed through these. Just a matter of getting them done because I think this is gonna clock in at 3.5, unfortunately. But anyways, those are all the reactions for this course. Or sorry, not for the course, I wish for the course, but for alkenes. I know it's a lot, but let's just quickly go back and do like a little bit of a clumping, sort of like let's kind of recap and sort of clump these together and see what it is we want to think about. But for most of these reactions, what you want to do is what are the similarities and how can I remember them, right? Because that's the biggest thing is we have so many reactions. How can I remember them? The first part of this, right, that we did all the acid mechanisms because the acid mechanisms are the same. You add a proton, make a cation can do some weird stuff, but after that, nucleophile adds on, right? So when you're thinking about your H+ reactions, right, we can think, for example, right, if I'm thinking my H+ reactions, right, you can think that a cation can form. And it can do some weird stuff like rearrange. And then my nucleophile adds on. Right? So cationic mechanisms, right? You can think about all the things that can do that, right? There is water that can do that. There is alcohol. All the halides can do it. Sulfur can do it, right? All the likes, right? These are the guys that would do it. So this is what you want to think for cationic mechanism. For the cyclics, right? What do we want to think? We want to think that, hey, cyclics do us a little favor. So we add in some atom A. And cyclics do us this favor that, they kind of trap the cation. They trap it in this membered ring that encompasses only the carbons of the pi bond. So when I do my reactions, I'm pretty much always forced to react only with those two carbons, right? It's just that sometimes, I will, keep A, sometimes I won't, but nucleophile adds on the more sub that's only indicative of that pi bond. So sometimes, again, we keep A, sometimes we don't, just up to remembering what it is. But these guys are going to be your mercuric acetates, X2, and MCPBA. Right? MCPBA being like sort of the hallmark of these. It's the one that explains all the reactivity on this. Right. Finally, the last like concrete group were the sort of less stable products, right? The ones that trick the molecule into adding a group G here, right? And forming some sort of, putting something here, but you trick the molecule into adding group G. And that group G, you turn into what you would have wanted as your nucleophile, right? And so this is your boration reaction and your HBr exclusive with peroxide. I think you can also do this with sulfthiols too. So I'll add this in just in case. But yeah, and then the last bit is just the oddballs, right? These guys kind of just do some reactions, right? And there's only 4 of them, although a lot of these have similar components to them, which is nice. So Right, we have H2PD. Right, send addition on that. Actually, let's just do it this way. Let's just do it with concepts. H2PD, we have carbene. Just keep in mind, right? Sometimes we can put chlorines here if we have the CH2Cl2 or CHCl3. Osmonium. I guess, again, sort of like the similarities is that they kind of form rings, right? These guys kind of, or they're, I want to say their transition states are kind of like rings, but I guess you can say that about a lot of these guys. Their transition states are kind of like rings. So yeah. I'm still thinking about ways of how to add these in. That makes sense. And then last but not least, O3, which hopefully now is makes a little more sense. Just like that. Cool. So this is sort of a quick breakdown of all the reactions, how to clump them, how to think about them. I think it's really this purple range that you'll probably spend the most time. But if you just think about these, like the concepts that we learned for these class of reactions, I think your life will be a lot easier in how to deal with these reactions. Now, in the last 5 minutes, I just want to talk about one more thing, just one more thing. Please bear with me for one more thing. And that is the idea of chemoselectivity. We actually talked a little bit about chemoselectivity earlier when we talked about borane, because we mentioned that when we do reactions with borane, for example, let's say we had like a dialkene here, or a diene, and we did a reaction with borane. Right, what would happen? Where would borane react? Again, let's do Br2H. Or sorry, R2 BH. Right, where would we see reaction? Well, borane is huge, so borane preferentially reacted here. So we would see reaction on the less sub alkene. Right, that's where we see reaction. It's on the least sub of all sub alkenes. Right. Well, we can extend this idea of chemoselectivity to a lot of reactions. If we just think about the intermediates and what's important to those intermediates, right, we can actually extrapolate a lot. So easiest one to start with actually is the proton mechanisms, because again, protons are going to form wherever they're most stable. And so if we have, I'll do a different example. Let's do this one here, right? Let's say we have this here, right? Disub versus tetrasub. Clearly the proton is always reacting over here. Right? So for your acid mechanisms, you're always going to get a more sub chemoselectivity, and that's where it's going to react. Okay. We can make the same argument, or sorry, I didn't mean to say same, but we can make a similar argument for this one here, but with the cyclics. So I'll just put A here, where A forms a cycle. Because A, although it isn't a carbocation, it's still a cation, and this cation draws a lot from the surrounding environment. So any reaction that does this will be preferred at that carbon or at that alkene. So just a reminder, this would be MCPBA next to, and I guess mercuric acetate. Yeah, I don't have to guess it. That is the case. Okay. Acid mechanism, that's like H2O, ROH, RSH, X minus, anything that you would do plus H plus, right? Any of these that you would add with H plus, that's the case. I guess to make things more congruent, then I'll do this. R2BH is really actually the only thing that does this actually. Right, that prefers to add on the less sub here. It's like the only one actually. Because if you think about it, no other compound preferentially went less sub like that. Even actually, even if you really think about it, even the peroxide addition would actually follow this. And the reason for that is because, remember, we're forming, even though we're going on a less sub carbon, right? What we're forming is, I think maybe it'll make more sense if I do this. Let's use this guy here for chemoselectivity. We're forming a radical on the more sub carbon, right? Even though the bromine is going here, it's just forming a radical on the more sub carbon. So chemoselectively, it's still reacting with that more sub carbon. Really, only boron is the one that reacts to less sub. That's the only one. Everything else reacts with the more sub. At the end of the day, there is always a couple that we don't really care about. Like for example, so we don't care about O3. We don't really care about carbene. We don't really care about probably not osmonium. I don't think you'll get any trouble with that one. And H2PD. H2PD actually reacts everywhere. So if there's multiple alkenes, it'll react at all possible spots. Actually, all of these typically, when you're doing them, it's because we want you to react them at all possible spots. Even osmonium, I guess osmonium maybe can fit into, maybe we can actually fit it in here. I'll go on a limb and say this is true, probably. That it reacts, but it'll react similar to these guys in that respect, actually. Maybe in the future, I'll add osmonium in this section here, even though it's not necessarily a cycle that we would want. Still a cycle. But yeah, cool. So just wanted to add this chemoselective part in here because it's something that we don't really talk about, but it is something we should at least consider. And that's it. That's it. That's going to be the reaction video. I apologize. I know this is over 3 hours and I didn't want it to be. So hopefully you guys can really get through this one with fast time. Cool. Oh, there was a problem I didn't solve, was there? No, I did solve them. I showed where they'd be reduced selectively. Yeah. So just a reminder, this was just, if you just look back here, this will explain all the answers to this one. The only thing is this one that's a little bit more difficult, but if you did concentrated acid, it would look like this. I guess it would look like this if it were a nucleophile. Yeah. Cool. All right. Have a good one, guys. See you in the next one.